The universe breathes in dimensions that curve back upon themselves, and in this first exhale after the beginning, time itself learns to flow. Space expands in all directions at once, but the directions include not only here and there, but also when and then. Light travels forward into futures that already exist, carrying information toward destinations that have been waiting since the moment expansion began. The cosmic microwave background radiation, that faint whisper left over from when atoms first formed, streams through space toward receivers that will not be built for billions of years. Yet the radiation knows where it is going. In these early moments, causality takes shape like cooling glass. Events arrange themselves in sequence, cause, then effect. But the sequence exists entire, like a river viewed from high above. The future pulls as much as the past pushes. Quantum fields fluctuate according to rules that encompass all of time. Each particle's position and momentum determined by equations that extend infinitely forward and back. The uncertainty principle operates not because the future is unknown, but because it contains all possibilities simultaneously, each outcome weighted by its probability, all of them equally real until observation collapses the wave function into a single thread of experienced time. Dark energy drives expansion at an accelerating rate, and this acceleration follows a curve that cosmologists will one day measure precisely. The curve already exists, mathematical and inevitable, describing how galaxies will separate from one another across eons. Space grows larger between distant objects, but the growth follows a script written in the fundamental constants, the cosmological constant. That mysterious force pushing the universe apart operates with perfect consistency toward a future it has already calculated. Every galaxy, every star, every mote of dust rides this expansion toward coordinates that space-time has already prepared for them. Gravity wells form where matter congregates, bending space-time into valleys and hills. But these aren't random formations. They follow the contours of possibility space, where certain arrangements become inevitable given the initial conditions. The seeds of future galaxies exist as tiny fluctuations in density, variations so small they barely register against the smooth background of early space. Yet these fluctuations contain within them the spiral arms of galaxies that will not form for hundreds of millions of years. The dark matter halos that will cradle these galaxies have already begun their patient work, gathering ordinary matter into configurations that the equations of gravitation have long since solved. Some theorists whisper that information cannot be destroyed, that every quantum state leaves permanent marks on the structure of space-time itself. If this is true, then the future already knows everything that will happen because the past has told it. Each photon carries data about its origin, its journey, its destination. The cosmic web forms according to patterns that respond to both past density fluctuations and future gravitational configurations. Matter flows toward places where it will eventually reside, following gradients in space-time that exist across all time. The first stars will ignite in regions where gas clouds have been converging since expansion began. These stellar nurseries operate on schedules written in the physics of gravitational collapse and nuclear ignition. The exact moment when each protostar reaches the temperature and pressure necessary for fusion has been predetermined by the initial mass distribution and the rate at which matter cools and condenses. The future watches as hydrogen atoms drift toward their eventual homes in stellar cores, where they will fuse into helium according to reaction rates that nuclear physics has already calculated. Light cones extend outward from every point in space-time, defining what can influence what and when. The future lies within the light cone of the present, connected by paths that information and energy can travel. But this connection works both ways. The future's light cone extends back into the past, encompassing all the events that will have contributed to its existence. Past and future interlock like fingers, each containing the other. The present moment exists at the intersection of all light cones, a point where every past and every future meet. Temperature fluctuations in the early universe create patterns that will determine the large-scale structure of space billions of years hence. Hot spots and cold spots in the primordial plasma mark regions of slightly higher and lower density. These variations, measured now as tiny differences in the cosmic microwave background, contain the blueprints for galactic superclusters, vast empty voids, and the filamentary networks that connect galaxy groups across cosmic distances. The universe carries its future geography written in these ancient temperature maps. Time flows like a river, but rivers can be viewed from above, their entire course visible at once. The future exists as surely as the past, laid out in the mathematics of space-time. Every equation in physics is time-symmetric. They work equally well, forward and backward. The arrow of time emerges from statistical considerations, from the fact that entropy increases and information spreads. But the underlying structure of reality encompasses all moments simultaneously. The future already exists, watching the past unfold according to the same laws that brought it into being. In quantum mechanics, particles can be influenced by future measurements through delayed choice experiments and quantum eraser configurations. The future state of a photon can determine the path it took in the past. This suggests that causality operates in both directions, that the future participates in creating the history that led to it. The universe may be solving itself backwards as well as forwards, each moment determined by the intersection of past causes and future constraints. What appears to be flowing time may be simply the way consciousness experiences a static four-dimensional structure that contains all events in their proper space-time coordinates. The cosmic web stretches its dark tendrils across distances that dwarf galaxies, and these filaments have been growing toward their final configuration since the universe was smooth and featureless. Dark matter, that invisible scaffolding that comprises most of reality's mass, flows along predetermined channels carved by gravity's patient mathematics. Each particle of dark matter follows trajectories calculated by the initial density fluctuations, moving toward intersections that will not occur for billions of years. Yet the intersections already exist as solutions to the differential equations that govern cosmic structure formation. Between the great filaments lie voids, vast spaces nearly empty of matter, where galaxies are rare and the expansion of space proceeds almost unimpeded. These voids grow larger as the universe ages, but their final sizes and shapes have been determined since the first moments after the Big Bang. The matter that does not flow into the cosmic web's bright nodes creates these cathedral spaces of near emptiness, regions where future civilizations might look out at a universe that appears almost barren. The voids know their own boundaries, expanding according to rules that balance the inward pull of distant matter with the outward push of dark energy. Dark matter halos form wherever the cosmic web's filaments intersect, creating gravitational wells deep enough to capture ordinary matter. But these halos grow according to a hierarchy that unfolds over cosmic time. Smaller structures merge to form larger ones in a process that cosmologists call bottom-up structure formation. The sequence of mergers follows a schedule written in the statistics of density fluctuations and the dynamics of gravitational collapse. Each halo knows which other halos it will eventually consume, and when these cosmic meals will occur. The largest galaxy clusters that will exist at the universe's maturity have been assembling their component pieces since matter first began to clump. Ordinary matter, the stuff of stars and planets and living things, makes up only a small fraction of the universe's total mass and energy. Yet this minority component follows the gravitational guidance of its dark companions, flowing along the same cosmic highways toward the same predetermined destinations. Gas clouds stream through intergalactic space along paths that will eventually deliver them to star-forming regions in galaxies that do not yet exist. The baryonic matter obeys the same equations as its dark counterpart, but it can radiate energy and cool, allowing it to collapse into denser configurations that will become the visible components of the cosmic web. Supermassive black holes grow at the centres of the largest dark matter halos, feeding on the matter that the cosmic web delivers to them. These black holes and their host galaxies co-evolve according to relationships that astrophysicists are still discovering, but the relationships themselves have been operating since the first black hole seeds formed in the early universe. The final masses of these objects have been determined by the amount of matter available in their local cosmic web nodes and the efficiency with which they can capture and accrete it. Future quasars sleep in present-day gas clouds, waiting for the gravitational focusing that will deliver fuel to their central engines. The cosmic web's filaments carry not only matter but also angular momentum, the tendency of things to spin. Galaxy clusters rotate slowly, their constituent galaxies orbiting around common centres of mass according to the net angular momentum that their cosmic web filament delivered to them. This rotation has been building up since the early universe, as matter flowing along slightly twisted paths accumulated its spin. The future orientations of galaxy clusters have been encoded in the subtle torques that the cosmic web's geometry imparts to infalling matter. Magnetic fields thread through the cosmic web's filaments, carried by the ionized gas that flows along these dark matter highways. These weak magnetic fields will eventually be amplified by the dynamo processes operating in galaxies and galaxy clusters. But their large-scale structure has been determined by the topology of the cosmic web itself. The magnetic field lines follow the filaments, creating a vast network of cosmic magnetism that connects distant regions of space. Future radio telescopes will map these fields and discover that they trace the same patterns as the dark matter distribution, revealing the electromagnetic skeleton of the universe. Some cosmologists suspect that the cosmic web structure contains information about the quantum fluctuations that seeded all cosmic structure. If the universe first underwent a period of rapid expansion called inflation, then quantum fluctuations in the inflaton field were stretched to cosmic scales and became the density variations that eventually grew into the cosmic web. This means that the web's pattern preserves a fossilized record of quantum events from the universe's first fraction of a second. The future structure of space was determined by quantum uncertainty in the earliest moments, randomness that became destiny through the amplifying effects of gravitational collapse. The cosmic web grows through accretion, but it also evolves through the feedback effects of the objects it creates. Star formation in galaxies generates winds that blow gas back out into the intergalactic medium. Supermassive black holes produce jets and radiation that heat the gas in their host galaxy clusters. These feedback processes regulate the rate at which the cosmic web can convert gas into stars, creating a self-regulating system that will eventually reach equilibrium. The final state of this equilibrium has been predetermined by the balance between gravitational collapse and stellar feedback, a balance that the equations of astrophysics have already calculated. Dark energy accelerates the expansion of space, but it affects different parts of the cosmic web differently. Regions that have not yet collapsed into gravitationally bound structures will be stretched apart by this accelerated expansion, while regions that have already collapsed will remain gravitationally bound. This creates a future universe in which the cosmic web's nodes become isolated islands in an increasingly empty sea of space. The final configuration has been determined by the competition between gravity and dark energy, a cosmic tug-of-war whose outcome was decided by the fundamental parameters of cosmology. Stars begin their lives as gravitational collapses in molecular clouds, but they carry within their cores the seeds of their own destruction. Nuclear fusion proceeds according to reaction rates that depend on temperature and density, and these rates determine not only how brightly a star will shine, but also how long it will live and how it will die. The most massive stars burn through their nuclear fuel in mere millions of years, while the smallest red dwarfs will continue fusing hydrogen for trillions of years. Long after the universe has grown cold and dark, each star's fate has been written in the physics of its initial mass, a stellar biography encoded in the gravitational collapse that brought it into being. The elements that will compose future planets and living beings are forged in stellar cores through fusion processes that operate on nuclear timescales. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on up the periodic table until iron forms in the deepest stellar furnaces. But iron cannot fuse to release energy. It represents the end of the nuclear road, the point at which fusion becomes endothermic rather than exothermic. Stars that reach this point face core collapse, and in their final moments they synthesize elements heavier than iron through rapid neutron capture processes. These stellar deaths scatter newly made atoms into space, seeding the interstellar medium with the raw materials for rocky planets and complex chemistry. Supernovae explosions operate like cosmic recycling plants, taking the simple hydrogen and helium that emerged from the Big Bang and converting them into the entire periodic table of elements. But each supernova follows a script determined by stellar evolution theory and the equations of nuclear physics. The exact moment when a massive star's iron core reaches the Chandrasekhar limit and collapses has been predetermined by the star's mass and composition and rotation rate, the energy released in the explosion, the elements synthesized, and the shockwave's impact on nearby gas clouds all follow from the fundamental physics of gravitational collapse and nuclear fusion. White dwarf stars represent the final state for stars like the Sun. Stellar corpses composed of carbon and oxygen held up by electron degeneracy pressure. These objects cool slowly over cosmic time, radiating away their thermal energy into space according to the laws of thermodynamics. The cooling curves of white dwarfs are so well understood that astronomers use them as cosmic clocks, measuring the ages of galactic stellar populations by examining their coolest white dwarf members. Each white dwarf carries within its temperature the history of when it formed, a stellar fossil whose future cooling rate has been calculated by atomic physics. Neutron stars form when stellar cores collapse beyond the white dwarf limit, crushing protons and electrons together into neutrons, and creating objects so dense that a teaspoonful would weigh as much as a mountain. These objects spin rapidly when they first form, conserving the angular momentum of their progenitor star's core in a much smaller volume. But magnetic braking gradually slows their rotation over millions of years, and this spin-down follows predictable patterns that allow astronomers to estimate neutron star ages. The magnetic fields of these objects decay according to exponential laws, their future field strengths already calculable from their present values and the physics of magnetic field diffusion. Black holes represent the ultimate endpoint of gravitational collapse, regions where space-time curves so severely that nothing can escape once it crosses the event horizon. But even black holes are not eternal. Stephen Hawking showed that they radiate energy through quantum effects at their boundaries, slowly evaporating over vast timescales. The evaporation rate depends on the black hole's mass, with smaller black holes radiating faster than larger ones. This means that the fate of every black hole in the universe has been predetermined by its mass. Stellar mass black holes will evaporate in about 10 circumflex 67 years, while supermassive black holes will take 10 circumflex 100 years to disappear completely. The stellar initial mass function describes the relative numbers of stars born at different masses, and this function appears to be nearly universal across different environments and cosmic times. More low-mass stars form than high-mass stars, following a power law that ensures most stars will be long-lived red dwarfs rather than short-lived blue giants. This distribution has profound implications for the future of galaxies. The longest-lived stars will continue shining long after star formation has ended, providing steady sources of energy for any civilizations that might exist in the far future. The demographics of stellar populations have been determined by the physics of stellar formation and the statistics of turbulent gas cloud collapse. Binary star systems evolve according to the complex interplay of stellar evolution and orbital dynamics. When one star in a binary system evolves faster than its companion, it can transfer mass to the other star, altering both objects' evolutionary paths. Some binaries will eventually merge, either through gravitational wave radiation that causes their orbits to decay, or through common envelope evolution that brings their cores together. The outcomes of these interactions have been mapped by stellar evolution codes that can calculate the future states of binary systems given their initial masses, compositions, and orbital separations. Planetary nebulae form when dying stars expel their outer layers into space, creating glowing shells of ionized gas illuminated by the hot white dwarf cores left behind. These nebulae expand into the interstellar medium according to the pressure balance between their internal energy and the ambient gas density. The expansion velocities and ionization structures of planetary nebulae follow predictable patterns that depend on the properties of their central stars and the surrounding environment. Each nebula carries within its structure the history of the mass loss episodes that created it, a record written in the velocities and compositions of its expanding gas shells. The chemical evolution of galaxies proceeds through the accumulation of stellar nuclear synthesis products over cosmic time. Each generation of stars adds more heavy elements to the interstellar medium, gradually enriching the gas from which future stars will form. This process follows well-understood patterns that depend on the star formation rate, the stellar initial mass function, and the efficiency with which stellar winds and supernova explosions mix newly synthesized elements into the surrounding gas. The future metallicity of galactic gas has been predetermined by these enrichment processes and the rate at which galaxies form new stars. Light travels at a constant speed through the vacuum of space. But in the expanding universe, This creates a peculiar relationship between distance and time. Photons from distant galaxies began their journeys billions of years ago, when the universe was younger and those galaxies were closer to us than they are now. The light we receive tonight from the most distant observable objects carries information about conditions that existed when the universe was only a few 100 million years old. These ancient photons have been travelling toward Earth across cosmic time, carrying messages from epochs that no longer exist anywhere except in the light itself. The cosmic microwave background represents the oldest light in the universe, released when atoms first formed about 380,000 years after the Big Bang. This radiation fills all of space with nearly uniform intensity, but tiny fluctuations in its temperature reveal the seeds from which all cosmic structure grew. The patterns in this ancient light encode information about the universe's geometry, composition, and initial conditions with extraordinary precision. Future cosmologists will continue to extract new insights from this fossil radiation, reading the universe's early history and temperature variations measured to millionths of a degree. Redshift stretches the wavelengths of light from distant sources as space expands during the photon's journey to Earth. This stretching provides a direct measure of cosmic expansion, allowing astronomers to reconstruct the universe's growth history by observing objects at different distances. The relationship between redshift and distance follows from the solutions to Einstein's field equations for an expanding universe, solutions that were derived decades before the observational evidence confirmed them. The future expansion of space has been encoded in the same equations, predicting how the redshift-distance relationship will change as dark energy continues to accelerate cosmic expansion. Type Ia supernovae serve as standard candles for measuring cosmic distances because they all reach nearly the same peak brightness when they explode. These explosions occur when white dwarf stars in binary systems accrete enough matter to exceed the Chandrasekhar limit, triggering thermonuclear detonation. The uniformity of their peak luminosity allows astronomers to determine their distances by comparing apparent and absolute brightness. Observations of distant Type Ia supernovae reveal that the universe's expansion is accelerating, driven by the mysterious dark energy that comprises about 70% of the cosmos. Gravitational lensing bends light rays from background sources when they pass through the curved space-time around massive foreground objects. This effect, predicted by general relativity, allows astronomers to map the distribution of dark matter in galaxy clusters and to discover exoplanets around distant stars. Strong lensing can create multiple images of the same background galaxy, while weak lensing subtly distorts the shapes of background galaxies in statistically detectable ways. The amount of lensing depends on the total mass along the light ray's path, providing a direct probe of matter distribution regardless of whether that matter emits light. The surface of last scattering represents the epoch when the universe became transparent to its own radiation. Before this time, the cosmos was hot and dense enough that electrons and protons existed as free particles, making space opaque to light through constant scattering. When the temperature dropped sufficiently for atoms to form, photons could travel freely through space for the first time. The cosmic microwave background carries the imprint of acoustic oscillations that were propagating through the plasma when this transition occurred. Frozen into the radiation at the moment of decoupling, quasar light provides a probe of the intergalactic medium through absorption line spectroscopy. As light from distant quasars travels toward Earth, it passes through intervening gas clouds that absorb specific wavelengths corresponding to electronic transitions in hydrogen and other elements. The resulting absorption lines create a forest of features in quasar spectra that map the distribution and properties of intergalactic gas over cosmic history. These observations reveal how the universe was reionized by the first stars and quasars, and how metals from stellar nuclear synthesis were distributed through intergalactic space. Neutrinos interact so weakly with matter that they can travel from the cores of stars directly to Earth without being absorbed or scattered. This makes them powerful probes of stellar interiors and explosive events like supernovae. The neutrinos produced by nuclear fusion in the Sun's core escape immediately and reach Earth in about 8 minutes, while the photons produced by the same reactions take thousands of years to random walk their way to the solar surface. Neutrino astronomy provides direct information about nuclear processes in stellar cores and the physics of core collapse supernovae. Cosmic rays consist of high-energy particles that travel through interstellar space at nearly the speed of light. These particles carry information about the extreme environments where they were accelerated, including supernova remnants, pulsar wind nebulae, and active galactic nuclei. The highest energy cosmic rays have energies that exceed anything achievable in terrestrial particle accelerators, providing a natural laboratory for studying physics under extreme conditions. The arrival directions and energy spectra of cosmic rays encode information about their sources and the magnetic fields they encountered during their journeys through space. Gamma-ray bursts represent the most energetic explosions in the universe since the Big Bang, releasing more energy in seconds than the Sun will produce in its entire lifetime. These events occur when massive stars collapse to form black holes, or when neutron stars merge in close binary systems. The afterglows of gamma-ray bursts can be detected across cosmic distances, providing beacons that illuminate the early universe. Some gamma-ray bursts occurred when the universe was less than 1 billion years old, offering glimpses of star formation and galaxy evolution during cosmic dawn. The integrated light from all stars that have ever shone creates a diffuse background radiation called the extragalactic background light. This faint glow permeates all of space and represents the accumulated stellar energy output over cosmic history. High-energy gamma rays from distant blazars interact with this background light through pair production, creating a cosmic speed limit for gamma rays that depends on their energy and the density of background photons. Measurements of this interaction provide constraints on the star formation history of the universe and the build-up of stellar mass over time. Each photon carries within its energy and polarization a record of every interaction it has experienced since its creation. The light from distant galaxies encodes information about the gas clouds it passed through, the gravitational fields that bent its path, and the expansion history of space during its journey. This information remains perfectly preserved until the moment of detection. When the photon's wave function collapses and its quantum state is measured, the universe's history travels toward us at the speed of light, arriving moment by moment as electromagnetic radiation from increasingly distant and ancient sources. Planetary orbits carve elliptical paths through space according to solutions that Johannes Kepler derived 4 centuries ago. But the mathematics extends far beyond his 3 laws into a celestial clockwork that ticks with perfect precision across geological ages. Each planet's position can be calculated for any moment in the past or future, using Newton's law of gravitation and the initial conditions that define the solar system's birth. The gravitational dance of worlds follows equations that contain no uncertainty, only the accumulated effects of countless tiny perturbations that shift orbital elements by imperceptible amounts over millions of years. The solar system's long-term stability depends on a delicate balance between gravitational resonances and chaotic perturbations. Computer simulations can track planetary motions forward in time for hundreds of millions of years before small uncertainties in initial conditions begin to dominate the calculations. Yet even chaos theory reveals that certain orbital configurations remain stable across cosmic time, while others lead inevitably to planetary ejections or collisions. The future architecture of the solar system has been constrained by these dynamical studies, which show that most planets will continue their current orbits until the Sun's evolution disrupts the entire system. Asteroid and comet orbits extend the gravitational calculations to millions of smaller bodies that populate the solar system. The minor planets follow the same physical laws as their larger cousins, but their smaller masses make them more susceptible to perturbations from planetary encounters and non-gravitational forces. The Yarkovsky effect slowly changes asteroid orbits as thermal radiation from their sun-warmed surfaces provides a tiny but persistent thrust. This effect operates so predictably that astronomers can calculate how it will alter potentially hazardous asteroid trajectories over the next several centuries. Tidal forces gradually modify planetary spins and orbital distances through the transfer of angular momentum between rotation and revolution. The Moon recedes from Earth by about 4 centimeters per year, as tidal friction slows our planet's rotation and transfers energy to lunar orbital motion. This process has been operating since the Moon's formation and will continue until Earth and Moon become tidally locked, with the same hemispheres always facing each other. The final orbital configuration has been calculated by celestial mechanics. The Moon will stabilise at about 1.6 times its current distance when the Earth-Moon day equals the lunar month. Binary star systems demonstrate orbital mechanics on a grander scale, with stellar companions dancing around their common centres of mass According to the same gravitational principles that govern planetary motion, close binary systems can exchange mass when one star evolves beyond its Roche lobe, the gravitational boundary that defines each star's sphere of influence. This mass transfer alters the orbital dynamics in complex ways that stellar evolution codes can model with remarkable precision. The future evolution of each binary system has been predetermined by the initial masses, compositions, and orbital separations of its component stars. Galactic orbits carry stars around the Milky Way's centre in paths that take hundreds of millions of years to complete. The Sun follows a nearly circular orbit at a distance of about 26,000 light-years from the galactic centre, moving at roughly 220 kilometers per second relative to the galaxy's centre of mass. This orbital motion has carried Earth through different regions of the galaxy over geological time, exposing our planet to varying cosmic ray fluxes and stellar densities that may have influenced the evolution of life. The Sun's galactic orbit can be traced backward and forward in time using models of the galaxy's gravitational field. Spiral density waves create the galaxy's majestic arm structure through gravitational perturbations that compress gas and trigger star formation as stellar orbits carry material through these regions of enhanced density. Individual stars do not remain in spiral arms throughout their lifetimes. Instead, they orbit through the arms periodically as density waves propagate around the galaxy at a different speed than stellar orbital motion. This process creates the illusion of permanent spiral structure while individual components continuously cycle through the pattern. The future evolution of spiral structure has been modelled using magnetohydrodynamic simulations that track gas dynamics and star formation over cosmic time. Precession slowly changes the orientations of planetary orbits and rotation axes over periods of thousands to millions of years. Earth's axial precession creates a 26,000-year cycle that affects the timing of seasons relative to orbital position, while orbital precession changes the eccentricity and orientation of our planet's elliptical path around the Sun. These cyclic changes combine with variations in orbital inclination to produce the Milankovitch cycles that drive long-term climate variations. The future phases of these astronomical cycles have been calculated with sufficient precision to predict ice age timing for the next several million years. Planetary ring systems evolve through complex interactions between gravitational forces, particle collisions, and electromagnetic effects. Saturn's rings consist of countless ice and rock particles that orbit according to Kepler's laws while experiencing mutual collisions and perturbations from the planet's many moons. Shepherd moons maintain sharp ring edges through gravitational resonances, while density waves propagate through ring material like ripples on a pond. The ring's future evolution has been modelled using N-body simulations that show how these delicate structures will change as they spread radially and lose mass to atmospheric drag. Three-body problems demonstrate that even simple gravitational systems can exhibit chaotic behaviour when more than two objects interact. The restricted three-body problem, where a small test particle moves in the gravitational field of two massive bodies, produces regions of stable and unstable motion that can be mapped using techniques from dynamical systems theory. Lagrange points represent equilibrium solutions, where gravitational forces balance exactly, creating stable parking places for spacecraft and natural reservoirs for asteroids and comets. These mathematical solutions were derived centuries before space missions began using them for practical applications. Relativistic effects introduce tiny corrections to Newtonian orbital mechanics that become important for high-precision calculations. Mercury's perihelion precession includes a small contribution from general relativity that cannot be explained by Newtonian gravity alone. GPS satellites must account for both special and general relativistic effects to maintain accurate timing, as their orbital motion and position in the Earth's gravitational field affect the rates of their atomic clocks. These relativistic corrections can be calculated exactly using Einstein's field equations, providing tests of fundamental physics while enabling practical space-based technologies. The seafloor spreads outward from mid-ocean ridges at rates that vary from centimetres to tens of centimetres per year. But these rates follow patterns that geophysicists can measure using magnetic striping preserved in oceanic crust. As new basalt forms at spreading centres, iron-bearing minerals align themselves with Earth's magnetic field before cooling and locking in the field's orientation. When the magnetic field reverses, subsequent basalt preserves the opposite polarity, creating parallel stripes of normal and reversed magnetization that extend away from the ridge axis like a geological barcode. This magnetic record allows scientists to reconstruct spreading rates over the past 200 million years and project them forward to calculate where continents will be positioned in the distant future. Continental drift operates according to the same principles that drive seafloor spreading, but continental plates move more slowly because they are thicker and less dense than oceanic crust. The Atlantic Ocean widens by about 2.5 centimetres per year as North America and Europe separate along the mid-Atlantic ridge. At this rate, the Atlantic will be roughly 250 kilometres wider in 10 million years, assuming current plate motions continue unchanged. But plate tectonics is not perfectly steady. Spreading rates can change as new plate boundaries form and old ones become inactive, creating complex patterns of continental motion that computer models attempt to predict over geological timescales. Subduction zones consume oceanic crust at rates that balance seafloor spreading, maintaining Earth's surface area constant as new ocean floor forms at ridges while old ocean floor descends into the mantle at trenches. The angle and rate of subduction depend on the age and density of the descending plate, with older, colder oceanic crust subducting more steeply than younger, warmer crust. These geometric relationships determine where volcanic arcs form and how much water gets carried into the mantle with subducting slabs. The future locations of volcanic activity have been mapped by modelling subduction zone dynamics and the pathways that subducted material follows as it sinks through the mantle. Hotspot volcanism creates chains of seamounts and volcanic islands as oceanic plates move over stationary mantle plumes that rise from deep within Earth's interior. The Hawaiian island chain demonstrates this process clearly, with active volcanism currently occurring over the Hawaiian hotspot, while older islands have been carried northwest by Pacific plate motion. The ages of Hawaiian volcanoes increase systematically with distance from the current hotspot location, providing a geological record of plate motion over the past 80 million years. The future of Hawaiian volcanism has been predicted by extrapolating current plate motions. The next Hawaiian island will form southeast of the Big Island in approximately 1 million years. Mountain building occurs where continental plates collide, creating complex patterns of folding, faulting, and uplift that can be modelled using the principles of rock mechanics and structural geology. The Himalayas continue to rise as the Indian plate pushes northward into Asia at a rate of about 5 centimetres per year. But this motion also triggers earthquakes along active fault systems that accommodate the collision's complex geometry. The future evolution of mountain belts depends on the balance between tectonic uplift and erosional denudation, with climate change potentially altering erosion rates and modifying the topographic evolution of collision zones. Sedimentary basins form where crustal subsidence creates space for sediment accumulation, following patterns that petroleum geologists have learned to predict by modelling the thermal and mechanical evolution of continental margins. As new oceanic crust cools and contracts after rifting, thermal subsidence gradually deepens offshore basins, while rivers deliver sediment from eroding continental areas. The thickness and distribution of sedimentary layers provide a record of subsidence history that can be used to calibrate basin models and predict how sedimentary systems will evolve in response to future changes in sea level and climate. Earthquake cycles reflect the build-up and release of tectonic stress along fault systems, creating periodic patterns of seismic activity that seismologists attempt to forecast using statistical models and physical understanding of fault mechanics. The San Andreas fault system accommodates about 35 millimeters per year of relative motion between the Pacific and North American plates. But this motion occurs through a combination of steady creep and sudden slip during earthquakes. Paleoseismic studies reveal that major earthquakes have occurred repeatedly on the same fault segments over thousands of years, providing insights into the long-term patterns of seismic hazard that emergency planners use to prepare for future events. Glacial isostasy demonstrates how Earth's crust responds to changing surface loads on timescales of thousands to tens of thousands of years. During ice ages, the weight of continental ice sheets depresses the underlying crust, while deglaciation allows the crust to rebound slowly toward its original elevation. This process continues long after ice sheets disappear. Scandinavia and eastern Canada are still rising today in response to deglaciation that ended over 10,000 years ago. The rate of post-glacial rebound follows exponential curves that geophysicists can model using the viscoelastic properties of mantle rocks. Sea level changes result from the complex interaction between thermal expansion of seawater, changes in ocean volume due to ice sheet growth and decay, and vertical motions of the seafloor caused by plate tectonics and glacial isostasy. Current sea level rise reflects both thermal expansion as oceans warm and ice sheet melting in Greenland and Antarctica. But future sea level changes will depend on the rates of ice sheet collapse and the continued thermal response of deep ocean waters. Geological records of past sea level changes provide calibration data for models that attempt to predict how coastal environments will change over the next several centuries. Mantle convection drives plate tectonics through slow circulation patterns that transport heat from Earth's interior to its surface. Hot material rises at mid-ocean ridges and hotspots, while cold material sinks at subduction zones, creating a global circulation system that operates on timescales of tens to hundreds of millions of years. Computer models of mantle convection can simulate the evolution of plate boundaries and predict how the current configuration of continents and oceans will change over the next supercontinent cycle. These models suggest that the Atlantic Ocean will eventually close as the Americas collide with Europe and Africa, forming a new supercontinent in approximately 250 million years. DNA molecules carry instructions that evolution has written across billions of years. But the genetic code anticipates futures that do not yet exist. Each organism's genome contains sequences that will prove adaptive under conditions that may not arise for thousands of generations. Sleeping genes that await environmental triggers to activate dormant survival strategies. The redundancy built into genetic codes protects against mutations while preserving the flexibility to respond to selection pressures that natural selection has not yet applied. Every species carries within its chromosomes the potential for evolutionary responses to challenges that evolution itself has already prepared for through the patient accumulation of genetic variation. Natural selection operates through differential reproduction across generations, but the selection pressures that shape current populations include future environmental conditions that organisms cannot directly perceive. Climate change, habitat destruction, and emerging diseases create selective environments that favour traits not currently advantageous, but which will become essential for survival. Some individuals within every population carry genetic variants that will prove beneficial under future conditions, their descendants eventually comprising the majority, while less adaptable lineages disappear. Evolution appears to prepare for futures it cannot predict through the simple mechanism of maintaining genetic diversity. Coevolution links the evolutionary trajectories of different species and relationships that extend far into the future. Flowering plants and their pollinators have shaped each other's anatomy and behaviour through millions of years of reciprocal adaptation, creating mutual dependencies that constrained both partners' evolutionary options. The timing of plant flowering must match pollinator life cycles, while pollinator anatomy must match flower structure, creating co-evolutionary locks that can persist across geological time. These relationships create evolutionary debts and credits that species pay and collect across generations, binding their futures together through the invisible threads of adaptive necessity. Molecular clocks measure evolutionary time through the accumulation of neutral mutations that occur at roughly constant rates across lineages. The differences in DNA sequences between related species reflect the time since they shared a common ancestor. Assuming mutation rates remain approximately constant over evolutionary time, these molecular timepieces allow biologists to calibrate phylogenetic trees and estimate when lineage splits occurred in the deep past. The same constant mutation rates that reveal evolutionary history also predict how genetic distances will increase in the future, providing timestamps for the gradual divergence of populations into separate species. Sexual selection creates evolutionary pressures that can override survival advantages, driving the evolution of elaborate displays and ornaments that may reduce individual fitness while increasing mating success. Peacock tails, antler size, and courtship behaviours evolve according to runaway selection processes that can continue indefinitely as long as the traits remain correlated with mate choice. These sexual arms races create some of the most rapid evolutionary changes observed in nature, but they also make species vulnerable to environmental changes that alter the costs and benefits of sexual displays. The future evolution of sexually selected traits depends on the continued operation of mate choice mechanisms and the environmental context that determines their survival costs. Adaptive radiations occur when lineages colonize new environments and rapidly diversify to fill available ecological niches. The explosive evolution of Darwin's finches in the Galapagos Islands demonstrates how quickly natural selection can reshape anatomy and behaviour when populations encounter novel environments. Each island's unique combination of food sources and habitat types selected for different beak shapes and feeding strategies, creating the diversity of finch species observed today. Similar radiations have occurred repeatedly throughout evolutionary history whenever lineages gain access to unexploited ecological opportunities. Gene flow between populations can either constrain local adaptation by introducing maladaptive alleles or enhance adaptive potential by increasing genetic variation available for selection. The balance between migration and selection determines whether populations can adapt to local conditions or remain genetically homogenized across their ranges. Small amounts of gene flow can prevent populations from adapting to local environments, while complete isolation can reduce genetic diversity and limit adaptive responses to environmental change. The future evolutionary trajectories of species depend critically on how habitat fragmentation and climate change alter patterns of gene flow between populations. Evolutionary constraints limit the possible directions that natural selection can take, creating predictable patterns in the evolution of complex traits. Developmental constraints arise from the genetic and molecular mechanisms that control embryonic development, making some evolutionary changes much more likely than others. Phylogenetic constraints reflect the evolutionary baggage that lineages carry from their ancestry. Mammals cannot evolve the ability to photosynthesize because they lack the developmental machinery to incorporate chloroplasts into their cells. These constraints create evolutionary channeling that makes certain outcomes inevitable while rendering others impossible. Extinction events punctuate evolutionary history by eliminating large fractions of existing species and creating new ecological opportunities for survivors. Mass extinctions reset evolutionary clocks by removing dominant lineages and allowing previously subordinate groups to radiate into vacant niches. The recovery from extinction events follows predictable patterns as ecosystems rebuild their complexity through the colonization of empty ecological space. Current human impacts on global ecosystems may be creating the conditions for the sixth mass extinction, which would reshape the future trajectory of evolution on Earth through the selective elimination of large-bodied, slow-reproducing species. Evolutionary arms races between predators and prey, parasites and hosts, and competitors drive continuous adaptation as each party evolves countermeasures to the other's strategies. The Red Queen hypothesis suggests that species must continuously evolve just to maintain their relative fitness as their biological enemies evolve in response. These co-evolutionary dynamics can create escalating cycles of adaptation and counter-adaptation that persist indefinitely, with neither side achieving permanent advantage. The future intensity of these evolutionary conflicts depends on the continued coexistence of the competing parties and the genetic variation available for adaptive responses. Horizontal gene transfer allows organisms to acquire genetic material directly from other species, rather than only through inheritance from parents. This process is particularly common among bacteria and archaea, which can rapidly spread antibiotic resistance genes and metabolic capabilities across distantly related lineages. Horizontal transfer accelerates evolution by allowing organisms to acquire complex adaptations instantly rather than evolving them gradually through mutation and selection. The future evolution of microbial communities will be shaped largely by horizontal transfer events that redistribute genetic innovations across taxonomic boundaries. Creating evolutionary networks rather than simple branching trees, ice sheets respond to orbital forcing through feedback mechanisms that operate on timescales of tens of thousands of years. But the climate system carries within its atmospheric circulation patterns the seeds of future glacial cycles. The eccentricity of Earth's orbit around the Sun varies with a period of about 100,000 years, modulating the intensity of seasonal contrasts that drive ice sheet growth and decay. When orbital eccentricity is high and northern hemisphere summer occurs at aphelion, reduced summer insolation allows winter snow to persist through multiple seasons, gradually building continental ice sheets that can eventually cover millions of square kilometres. The astronomical theory of ice ages predicts that the next glacial maximum will occur in approximately 50,000 years, assuming current orbital mechanics continue unchanged. Atmospheric carbon dioxide concentrations fluctuate in concert with glacial cycles, but the relationship between ice volume and greenhouse gas levels creates complex feedback loops that amplify orbital forcing. Ice cores from Antarctica preserve a detailed record of atmospheric composition over the past 800,000 years, revealing that CO2 levels dropped to around 180 parts per million during glacial periods and rose to about 280 ppm during interglacials. These variations result from changes in ocean circulation, terrestrial vegetation, and ice sheet dynamics that alter the global carbon cycle in response to orbital forcing. Current atmospheric CO2 levels exceed 400 ppm and continue rising due to human activities, potentially overriding the orbital controls that have regulated ice ages for the past several million years. Ocean circulation patterns reorganize during glacial transitions as changing ice sheet configurations alter atmospheric pressure systems and wind patterns. The thermohaline circulation that currently transports warm water northward in the Atlantic Ocean can weaken or shut down entirely when fresh water from melting ice sheets reduces surface water density and prevents deep water formation. Paleoceanographic records show that these circulation changes occurred repeatedly during past glacial cycles, creating rapid climate transitions that could shift regional temperatures by several degrees within decades. The future stability of ocean circulation depends on the rate of ice sheet melting and the amount of fresh water input to key deep water formation regions. Continental ice sheets grow through the accumulation of snow that persists from year to year, but ice sheet dynamics create their own climate through elevation and albedo feedbacks that can accelerate or decelerate their growth. As ice sheets thicken, their surfaces rise to higher, colder elevations where snow accumulation increases and melting decreases. The high albedo of ice and snow reflects incoming solar radiation back to space, cooling regional temperatures and creating conditions that favour further ice sheet expansion. These positive feedbacks can drive ice sheet growth even after the orbital forcing that initiated glaciation has weakened, creating hysteresis effects that make ice sheets persist longer than the climate changes that created them. Sea level dropped by more than 100 metres during the last glacial maximum as water evaporated from the oceans became locked in continental ice sheets. This exposure of continental shelves connected land masses that are now separated by shallow seas, allowing terrestrial species to migrate between continents and creating land bridges that shaped patterns of human and animal dispersal. The Bering Land Bridge connected Asia and North America when sea level was low, enabling the colonization of the Americas by humans and other species. Future glacial cycles will recreate these land connections while isolating regions that are currently connected, reshaping global biogeography through the cyclical rise and fall of sea level. Permafrost zones expanded during glacial periods as year-round freezing temperatures extended far south of their current limits. Permanently frozen ground now underlies about 25% of the Northern Hemisphere's land surface, storing vast quantities of carbon in frozen organic matter that accumulated over thousands of years. Climate warming threatens to thaw this permafrost and release its stored carbon as carbon dioxide and methane, creating a positive feedback that could accelerate future warming. The future extent of permafrost depends on both global temperature changes and local factors such as vegetation cover, soil moisture, and snow depth that modulate ground temperature. Vegetation zones shifted latitudinally during glacial cycles as temperature and precipitation patterns changed in response to altered atmospheric circulation. Tropical rainforests contracted to refugial areas during glacial periods, while grasslands and temperate forests expanded into regions that are now desert or tundra. These vegetation changes altered the global carbon cycle by changing the amount of carbon stored in terrestrial ecosystems and the rate at which organic matter was transferred to soils and sediments. Pollen records from lake sediments provide detailed reconstructions of past vegetation changes and serve as analogues for understanding how ecosystems might respond to future climate changes. Desert expansion during glacial periods reflected changes in the global water cycle as reduced evaporation from colder oceans decreased global precipitation, while altered atmospheric circulation patterns shifted storm tracks away from currently arid regions. The Sahara Desert expanded significantly during glacial maxima, reaching the Atlantic coast and creating dust sources that fertilized Amazon rainforests with windblown nutrients. These teleconnections between distant regions demonstrate how Ice Age climate changes propagated around the globe through atmospheric and oceanic circulation changes. Future climate changes may reactivate similar long-distance linkages between ice sheets, deserts, and tropical ecosystems. Mountain glaciers advanced during glacial periods as cooler temperatures and altered precipitation patterns favoured ice accumulation at high elevations. Alpine glaciers left detailed geomorphological records of their past extent through moraines, U-shaped valleys, and other erosional features that allow glacial geologists to reconstruct Ice Age climate changes in mountainous regions. Current mountain glacier retreat provides a visible indicator of ongoing climate change, while also serving as a natural experiment for understanding how glacial systems respond to warming temperatures. The future of mountain glaciation depends on both temperature and precipitation changes, with some regions potentially experiencing glacier growth if increased snowfall offsets warming temperatures. Atmospheric dust levels increase dramatically during glacial periods, as expanded desert areas and exposed continental shelves provided new sources of wind-blown particles. Ice cores contain detailed records of past dust deposition that reveal how atmospheric circulation changes affected the transport of mineral aerosols around the globe. Dust particles can influence climate by scattering incoming solar radiation and serving as cloud condensation nuclei that affect precipitation patterns. The fertilization effects of dust on marine and terrestrial ecosystems may have played important roles in glacial carbon cycle changes by stimulating biological productivity in nutrient-limited regions. Sedimentary layers accumulate grain by grain according to the rhythm of geological processes, but each stratum contains within its mineral composition and fossil content a record of environmental conditions that will not be fully decoded for centuries to come. River deltas build seaward through the deposition of eroded continental material, creating sequences that preserve information about ancient climates, tectonics, and biological communities in their vertical succession. The Grand Canyon exposes nearly 2 billion years of Earth history in its layered walls, each formation representing millions of years of deposition under conditions that geologists are still learning to interpret. Future advances in analytical techniques will continue extracting new information from these ancient archives, revealing details about past environments that current methods cannot detect. Turbidity currents transport sediment from continental margins to deep ocean basins into episodic flows that can cover thousands of square kilometers of seafloor with single depositional events. These underwater avalanches follow submarine canyons and spread across abyssal plains, creating graded beds that preserve records of their flow dynamics in the size, distribution, and orientation of transported particles. The timing and magnitude of turbidity currents depend on factors such as sea level changes, earthquake frequency, and sediment supply rates that vary over geological time. Turbidite sequences provide natural laboratories for understanding sediment transport processes and calibrating models that predict how future changes in climate and tectonics will affect deep-sea sedimentation. Chemical weathering rates control the pace at which continental rocks dissolve and release their constituent elements to rivers and eventually to the oceans. The intensity of chemical weathering depends on temperature, precipitation, and biological activity, creating feedback relationships between climate and the rock cycle that operate over millions of years. During warm, humid periods, accelerated weathering removes carbon dioxide from the atmosphere through the formation of carbonate minerals, providing a natural thermostat that helps stabilize Earth's climate over geological time. Future weathering rates will respond to changing temperature and precipitation patterns, while also being affected by human activities such as land use changes and acid precipitation. Carbonate platforms grow upward and outward as coral reefs and other marine organisms precipitate calcium carbonate from seawater, but their growth rates depend on water temperature, chemistry, and clarity in ways that make them sensitive recorders of past oceanic conditions. The internal structure of ancient reef systems preserves information about sea level changes, ocean acidification events, and mass extinction episodes that can be read like tree rings in the organisation of coral growth bands and the diversity of fossil assemblages. Modern coral reefs face threats from ocean warming and acidification that may provide insights into how ancient reef systems responded to similar environmental stresses during past climate change events. Evaporite deposits form when restricted marine basins lose water faster than they can replace it, concentrating dissolved salts until minerals such as halite and gypsum precipitate from the supersaturated brines. These chemical sediments preserve records of ancient climate conditions and ocean chemistry that extend back hundreds of millions of years. The formation of evaporites requires specific combinations of climate, tectonics, and ocean circulation that create the restricted basin geometries necessary for brine concentration. Future evaporite formation will depend on how climate change affects precipitation patterns and ocean circulation in marginal marine environments. Glacial deposits create distinctive sedimentary signatures that allow geologists to identify ancient ice ages in the rock record. Tillites, dropstones, and varved lake sediments preserve evidence of past glaciations that occurred throughout Earth history, including snowball Earth events when ice sheets may have extended to tropical latitudes. The distribution and timing of glacial deposits provide constraints on past continental positions and climate conditions that help calibrate models of long-term climate evolution. Current anthropogenic climate change may be altering the geological record in ways that will be recognizable to future geologists studying early 21st century sediments. Volcanic ash layers serve as time markers that allow geologists to correlate sedimentary sequences across vast distances and establish precise chronologies for past events. Major volcanic eruptions distribute ash over areas spanning thousands of kilometers, creating synchronous depositional events that appear as thin but widespread layers in sedimentary records. The chemical fingerprints of volcanic ashes can be used to identify their source volcanoes and establish eruption chronologies that provide temporal frameworks for understanding rates of environmental change. Future volcanic eruptions will continue adding time markers to the geological record while also potentially affecting global climate through their atmospheric impacts. Magnetic reversals create natural chronometers preserved in the magnetic orientations of iron-bearing minerals in sedimentary rocks. The polarity timescale established through magnetostratigraphic studies provides a global chronological framework that allows precise dating of sedimentary sequences and correlation between marine and continental records. Magnetic field behavior during polarity transitions may also preserve information about deep Earth processes and the dynamics of the geodynamo that generates Earth's magnetic field. Future magnetic reversals will continue providing chronological markers, while also potentially affecting technological systems and biological organisms that rely on magnetic navigation. Isotopic ratios in sedimentary rocks preserve information about past climate conditions, ocean chemistry, and biological productivity through the preferential incorporation of different isotopes during chemical and biological processes. Oxygen isotope ratios in marine fossils record ancient ocean temperatures and ice volumes, while carbon isotope ratios reflect changes in the global carbon cycle and biological productivity. These geochemical proxies allow quantitative reconstructions of past environmental conditions that can be compared with climate model simulations and used to evaluate the sensitivity of Earth systems to external forcing. Future developments in isotope geochemistry will continue expanding the range of environmental variables that can be reconstructed from the sedimentary record. Sequence stratigraphy reveals how sedimentary packages are organized by cyclical changes in sea level that reflect the interplay between global ice volume, thermal expansion of seawater, and regional tectonics. Unconformities mark time gaps in the sedimentary record where erosion or non-deposition occurred, often corresponding to sea level low stands when continental margins were exposed to sub-aerial weathering. The architecture of sedimentary sequences provides information about the rates and magnitudes of past sea level changes that can be used to understand how ice sheets and ocean basins responded to climate forcing. Future sea level changes will create new sequence boundaries while modifying the preservation potential of sediments currently being deposited in marine and coastal environments. Earth's magnetic field originates in the liquid iron outer core, where convective motions generate electrical currents that sustain the geodynamo. But this protective shield around our planet operates according to principles that include its own eventual reversal. The magnetic poles drift continuously as the field-generating processes in the core respond to thermal and compositional convection patterns that evolve over thousands of years. Paleomagnetic records preserved in volcanic rocks and sediments reveal that the field has reversed its polarity hundreds of times throughout geological history, with the north and south magnetic poles switching positions during transition periods that can last several thousand years. The next reversal may already be in progress, as the magnetic North Pole has been accelerating its drift across the Arctic at rates that have increased from about 15 kilometers per year to over 50 kilometers per year during the past few decades. Magnetic field intensity varies on multiple timescales as the geodynamo responds to changes in core dynamics and heat flow patterns from the deep mantle. The dipole component of Earth's magnetic field has been weakening at a rate of about 5% per century over the past 150 years, leading some geophysicists to speculate that this decline may herald the onset of a polarity reversal. However, the field has strengthened and weakened many times in the past without reversing, and the current decline may simply represent normal fluctuations in geodynamo intensity. Computer simulations of the geodynamo show that field reversals occur spontaneously in magneto-hydrodynamic models without requiring external triggers, suggesting that polarity transitions are an inherent feature of planetary magnetic field generation. The South Atlantic anomaly represents a region where Earth's magnetic field is significantly weaker than expected, for a simple dipole configuration, creating a zone where spacecraft electronics are more vulnerable to radiation damage from trapped particles in the Van Allen belts. This anomaly has been growing and intensifying over the past several decades, possibly indicating the emergence of a reversed flux patch that could eventually propagate around the globe and trigger a complete polarity reversal. Satellite measurements of the magnetic field provide unprecedented detail about the three-dimensional structure of these anomalous regions and their rates of change, offering insights into the deep core processes that control magnetic field evolution. Magnetic secular variation describes the slow changes in field direction and intensity that occur at any location as the global magnetic field evolves over time. Navigation charts must be updated regularly to account for these changes. As magnetic declination, the angle between magnetic north and true north, shifts by fractions of a degree per year at most locations. Archaeological artifacts such as pottery and hearths preserve records of past magnetic directions when iron-bearing minerals aligned with the field during their final cooling, creating an archaeological magnetic record that extends back several millennia in some regions. These records reveal that secular variation includes both gradual trends and abrupt changes that may reflect sudden reorganizations of flow patterns in the outer core. The magnetosphere deflects most solar wind particles around Earth, but magnetic reconnection events allow some solar material to penetrate the magnetospheric boundary and interact with the upper atmosphere. During magnetic storms triggered by solar coronal mass ejections, enhanced particle precipitation can disrupt radio communications, damage satellite electronics, and create aurora displays at latitudes much lower than their usual polar occurrence. The intensity and frequency of magnetic storms depend on solar activity cycles and the orientation of the interplanetary magnetic field carried by the solar wind. Future space weather events will continue affecting technological systems as human civilization becomes increasingly dependent on satellite-based communications and navigation systems. Paleomagnetism provides a tool for reconstructing past continental positions and testing theories of plate tectonics through the analysis of magnetic directions preserved in ancient rocks. When igneous rocks cool below their Curie temperatures, magnetic minerals lock in the direction of the ambient magnetic field, preserving a record of both the field direction and the rock's orientation relative to the magnetic poles. Apparent polar wander paths traced by paleomagnetic directions from different continents reveal how these land masses have moved relative to the magnetic poles over geological time. The convergence of apparent polar wander paths from different continents provides strong evidence for continental drift and helps constrain the timing and geometry of past supercontinent configurations. Magnetic anomalies over oceanic crust create parallel stripes of normal and reversed polarity that provide the most convincing evidence for seafloor spreading and plate tectonics. As new oceanic crust forms at mid-ocean ridges, iron-bearing minerals in the cooling basalt record the polarity of Earth's magnetic field at the time of their formation. Subsequent magnetic reversals create a symmetric pattern of magnetic stripes on either side of spreading centers, with the width of each stripe proportional to the spreading rate and the duration of the corresponding polarity interval. This magnetic striping allows geophysicists to reconstruct spreading histories and calculate past plate motions with remarkable precision. Core mantle boundary interactions may influence both magnetic field generation and mantle convection through thermal and chemical exchanges between the liquid outer core and the solid mantle. Large low-shear velocity provinces detected by seismic tomography near the base of the mantle may represent chemically distinct regions that affect heat flow patterns at the core mantle boundary. These heterogeneities could influence the locations where upwelling and downwelling occur in the outer core, potentially affecting the geometry of the magnetic field generated by core convection. The correlation between magnetic field features and mantle structure suggests that deep Earth processes operate as a coupled system over geological time. Lightning generates electromagnetic pulses that propagate around the globe in the Earth ionosphere waveguide, creating natural radio signals that can be used to monitor magnetic field variations and ionospheric conditions. These Whistler waves and other electromagnetic phenomena provide information about the electrical properties of the upper atmosphere and their response to solar activity and magnetic storms. Artificial radio transmissions for navigation and communication systems can also serve as probes of ionospheric conditions, revealing how space weather affects the propagation of electromagnetic signals through this magnetosphere and ionosphere. Magnetic minerals in sedimentary rocks record not only the direction of ancient magnetic fields, but also their intensity through the efficiency with which magnetic particles align during deposition. Relative paleointensity records from marine sediments reveal that Earth's magnetic field has varied in strength by factors of 2 to 10 over the past several million years, with intensity minima often associated with polarity reversals. These records suggest that the geodynamo operates in different modes characterized by distinct field intensities and reversal frequencies, possibly reflecting changes in core convection patterns driven by thermal evolution and core mantle interactions over geological time. Ocean currents flow through three-dimensional pathways that connect surface waters with abyssal depths, carrying heat, salt, and nutrients along routes that the physics of fluid motion have calculated centuries in advance. The thermohaline circulation operates like a vast conveyor belt driven by density differences created when surface waters cool and evaporate at specific latitudes, becoming dense enough to sink into the deep ocean and begin journeys that can last over 1,000 years. North Atlantic. Deep water forms in the Labrador and Greenland seas, where winter cooling and evaporation increase seawater density until it cascades over sills and spreads southward through the Atlantic basin. This same water mass will eventually upwell in the Pacific and Indian Oceans after following deep western boundary currents around Africa and through the Southern Ocean's circumpolar flow. The Gulf Stream carries warm water northward along the North American coast at speeds reaching several meters per second, transporting as much energy as millions of power plants, while following a path determined by the balance between pressure gradients, Coriolis forces, and bottom topography. This current system extends from the Florida Straits to the Grand Banks of Newfoundland, where it separates from the continental margin and becomes the North Atlantic current that continues toward Europe. The heat transported by this current system moderates European climate and affects weather patterns across the entire North Atlantic region. Climate models predict that future changes in Arctic ice melt and precipitation patterns could weaken this circulation system by reducing the density contrasts that drive deep water formation. Antarctic circumpolar current encircles the entire Southern Ocean, connecting the Atlantic, Pacific, and Indian Ocean basins through the only latitude band where currents can flow completely around the globe without encountering continental barriers. This massive current system transports more water than all the world's rivers combined, while mixing waters from different ocean basins and allowing heat and chemical traces to spread between the major ocean basins. The circumpolar current's strength depends on the westerly winds that blow across the Southern Ocean, creating a direct connection between atmospheric circulation patterns and ocean transport that affects global climate on timescales ranging from years to millennia. Upwelling systems bring deep, nutrient-rich water to the surface along certain coastlines, where offshore winds and the Coriolis effect combine to drive surface waters away from shore. The California Current, Benguela Current, and other eastern boundary upwelling systems support some of the world's most productive marine ecosystems by delivering nutrients that fuel phytoplankton blooms and support entire food webs. The strength and timing of coastal upwelling vary with seasonal wind patterns and longer-term climate cycles, such as El Niño, creating fluctuations in marine productivity that affect fish populations and seabird colonies throughout the Pacific Basin. El Niño Southern Oscillation represents a coupled atmosphere-ocean system that oscillates between warm El Niño and cool La Niña conditions, with periods ranging from 2 to 7 years. During El Niño events, weakened trade winds allow warm water to spread eastward across the Pacific, suppressing upwelling along the South American coast and altering precipitation patterns around the globe. La Niña conditions intensify the normal circulation patterns, strengthening upwelling and enhancing the temperature contrast between the eastern and western Pacific. These oscillations affect weather and climate worldwide through teleconnections that link tropical Pacific sea surface temperatures to storm tracks, precipitation patterns, and temperature anomalies in regions thousands of kilometers away. Deep water formation occurs in only a few locations worldwide where specific combinations of temperature, salinity, and topography create conditions for surface waters to become dense enough to sink to abyssal depths. The Greenland and Labrador Seas, the Weddell and Ross Seas around Antarctica, and the Mediterranean Sea represent the primary sources of the deep and bottom waters that fill the world's ocean basins. Changes in precipitation, evaporation, and ice melt can alter the salinity and temperature of surface waters in these regions, potentially disrupting deep water formation and reorganizing global ocean circulation patterns within decades. Oceanic gyres create large-scale circulation patterns in each ocean basin through the combined effects of wind stress, pressure gradients, and the Coriolis force. The North Atlantic and North Pacific gyres rotate clockwise while Southern Hemisphere gyres rotate counterclockwise, creating convergent zones where floating debris accumulates and divergent zones where nutrients upwell to support marine productivity. These gyre circulations transport heat poleward along their western boundaries and equatorward along their eastern boundaries, creating asymmetric temperature distributions that affect regional climate patterns and marine ecosystem dynamics. Tidal currents result from the gravitational pull of the Moon and Sun, creating periodic flows that can reach several meters per second in coastal areas with complex topography. The timing and strength of tidal currents follow astronomical cycles that can be predicted centuries in advance using harmonic analysis of the various periodic components. In some locations, tidal bores create waves that travel upstream in rivers when high tides encounter shallow water and constricted channels. The energy dissipated by tidal friction gradually slows Earth's rotation, while increasing the Moon's orbital distance, creating long-term changes in the length of days and months over geological time. Internal waves propagate through the ocean's stratified interior when density differences create interfaces that can support wave motion. These waves can have amplitudes of hundreds of meters and wavelengths of tens of kilometers, while remaining invisible at the surface. Internal wave breaking provides much of the energy needed to mix deep ocean waters and maintain the density structure that drives thermohaline circulation. The generation, propagation, and dissipation of internal waves depend on tidal forcing, wind stress, and topographic interactions that create complex energy cascades from large-scale currents to small-scale turbulence. Ocean acidification occurs as seawater absorbs increasing amounts of carbon dioxide from the atmosphere, forming carbonic acid that lowers seawater pH and reduces the availability of carbonate ions needed for shell and skeleton formation by marine organisms. The ocean has absorbed about 30% of the carbon dioxide emitted by human activities, causing pH to decline by 0.1 units since pre-industrial times. This acidification will continue as atmospheric CO2 concentrations rise, potentially affecting coral reefs, shellfish, and other calcifying organisms that form the base of marine food webs. The rate and magnitude of future acidification depend on emission scenarios and the ocean's capacity to buffer pH changes through carbonate chemistry. The atmosphere circulates in patterns that meteorologists can predict days in advance. But these same circulation systems operate according to thermodynamic principles that have already determined the climate's response to changing greenhouse gas concentrations over the next several centuries. Carbon dioxide molecules absorb infrared radiation emitted by Earth's surface, trapping heat that would otherwise escape to space and gradually warming the entire climate system. The relationship between atmospheric CO2 concentration and global temperature follows logarithmic curves that, Climate scientists have derived from both theoretical radiative transfer calculations and empirical observations of past climate changes. Current CO2 levels exceed 420 parts per million and continue rising at rates of about 2.5 ppm per year, committing the planet to additional warming even if emissions were to stop immediately. Water vapour amplifies greenhouse warming through feedback mechanisms that operate automatically as temperatures rise. Warmer air can hold more moisture, and since water vapour is itself a greenhouse gas, increased atmospheric humidity enhances the warming effect of other greenhouse gases. This positive feedback roughly doubles the warming that would occur from CO2 increases alone. But the magnitude of the water vapour feedback depends on how clouds respond to changing humidity and temperature patterns. High clouds tend to warm the surface by trapping outgoing infrared radiation, while low clouds tend to cool the surface by reflecting incoming solar radiation. The net effect of cloud feedbacks remains one of the largest uncertainties in climate projections, but most evidence suggests that clouds will provide modest positive feedback that amplifies greenhouse warming. The carbon cycle moves CO2 between the atmosphere, oceans, vegetation, and soils through exchanges that operate on timescales ranging from years to millennia. Terrestrial photosynthesis removes about 120 billion tons of carbon from the atmosphere each year, while plant and soil respiration returns nearly the same amount, creating a large but roughly balanced annual cycle. Ocean-atmosphere exchanges are similarly large, with cold waters absorbing CO2 and warm waters releasing it according to Henry's law, and the temperature dependence of gas solubility. Human fossil fuel combustion has disrupted this natural balance by adding about 10 billion tons of carbon to the atmosphere annually, an amount that exceeds the natural system's capacity for immediate absorption. Atmospheric residence times determine how long different greenhouse gases remain in the atmosphere after their emission. CO2 has no single atmospheric lifetime because it exchanges continuously with the oceans and biosphere, but the time required to remove excess CO2 from the atmosphere ranges from decades to millennia, depending on the processes involved. Ocean uptake operates on centennial timescales as surface waters mix with deeper layers, while rock weathering provides the ultimate sink for atmospheric CO2 on timescales of hundreds of thousands of years. Methane has a much shorter atmospheric lifetime of about 9 years, but is much more potent per molecule, creating opportunities for rapid climate benefits from methane emission reductions. Ice albedo feedback accelerates warming in polar regions as melting ice and snow expose darker surfaces that absorb more solar radiation. Arctic sea ice reflects about 80% of incoming sunlight, while the dark ocean surface underneath reflects only about 6%, creating a strong positive feedback as warming reduces ice cover and exposes more heat-absorbing ocean water. This feedback has contributed to Arctic warming rates that are roughly twice the global average, a phenomenon known as Arctic amplification. Similar feedbacks operate on land as warming temperatures cause earlier snowmelt and expose darker vegetation and soil surfaces that absorb more solar energy. Permafrost thaw releases stored carbon as warming temperatures penetrate deeper into previously frozen soils that contain vast amounts of organic matter accumulated over thousands of years. Northern permafrost regions contain an estimated 700 billion tons of carbon, roughly twice the amount currently in the atmosphere. As permafrost thaws, microbial decomposition converts this organic matter into CO2 and methane, creating another positive feedback that amplifies greenhouse warming. The rate of permafrost carbon release depends on local temperature changes, soil moisture, and vegetation dynamics that vary across the circumpolar Arctic. But climate models suggest that permafrost regions will transition from carbon sinks to carbon sources during the 21st century. Precipitation patterns change as warming alters atmospheric circulation and increases the water-holding capacity of air. The Clausius-Clapeyron relation shows that atmospheric moisture content increases by about 7% for each degree of warming, potentially intensifying both droughts and heavy precipitation events as the water cycle accelerates. Storm tracks may shift poleward as the temperature gradient between equator and poles weakens, bringing precipitation changes to regions that depend on specific seasonal rainfall patterns. These hydrological changes will affect agriculture, water resources, and natural ecosystems in ways that depend on local topography, vegetation, and human land use patterns. Ocean heat content increases as the climate system's thermal inertia delays the full surface warming response to greenhouse gas increases. The oceans contain over 1,000 times more heat capacity than the atmosphere, allowing them to absorb vast amounts of thermal energy while warming much more slowly than the overlying air. About 90% of the excess heat trapped by greenhouse gases has been absorbed by the oceans, delaying atmospheric warming but creating thermal expansion that contributes to sea level rise. The deep ocean will continue warming for centuries after surface temperatures stabilise, creating committed sea level rise from thermal expansion alone. Tipping points represent thresholds where climate system components transition rapidly between different stable states, potentially creating irreversible changes that persist long after the original forcing is removed. The West Antarctic ice sheet may have a tipping point beyond which marine ice sheet instability causes unstoppable ice loss, and several meters of sea level rise over centuries to millennia. The Amazon rainforest could reach a tipping point where reduced precipitation and increased fires convert large areas from forest to grassland, releasing stored carbon and eliminating a major carbon sink. These potential tipping points create risks of accelerated climate change that exceed projections based on gradual, linear responses to greenhouse gas increases. Geoengineering proposals attempt to counteract greenhouse warming through deliberate interventions in the climate system, either by removing CO2 from the atmosphere or by reducing incoming solar radiation. Solar radiation management could theoretically cool the planet by injecting reflective particles into the stratosphere or by brightening marine clouds. But these approaches would not address ocean acidification and could create uneven regional climate changes. Carbon dioxide removal technologies could directly address the root cause of climate change, but would require deployment at scales comparable to the current fossil fuel industry to significantly affect atmospheric CO2 concentrations. Mountain ranges rise according to the balance between tectonic forces that push rock upward and erosional processes that wear it down. But the mathematics of this competition have already calculated the maximum heights that peaks can achieve under different climatic and geological conditions. The Himalayas continue growing as the Indian plate pushes northward into Asia at about 5 centimeters per year, but their ultimate elevation will be limited by the strength of crustal rocks and the efficiency of erosional processes that increase with altitude. Glacial erosion operates more rapidly than river erosion in high mountain environments, creating positive feedback where taller peaks generate more snow and ice that enhance their own destruction. The equilibrium between uplift and erosion establishes characteristic mountain heights that depend on local climate, rock type, and tectonic setting. Isostatic adjustment causes mountain ranges to rise further as erosion removes mass from their summits and reduces the downward pressure on the underlying crust. This process operates like a ship unloading cargo. As weight is removed from the top, the entire crustal block floats higher on the underlying mantle. The Canadian Shield continues rising today in response to ice sheet removal that occurred over 10,000 years ago, demonstrating how slowly the solid Earth responds to changing surface loads. Future mountain building will involve similar isostatic responses as continued erosion reduces mountain mass and allows deeper crustal roots to rise toward the surface. Fold and thrust belts form where convergent tectonic forces compress and shorten continental crust, creating complex geometries that structural geologists can unravel using principles of rock mechanics and kinematic analysis. The Appalachian Mountains preserve a record of multiple orogenic events that occurred over hundreds of millions of years as ancient continents collided and separated repeatedly. Each collision event created distinctive structural styles and metamorphic patterns that reflect the temperature and pressure conditions during mountain building. These ancient mountain belts provide natural laboratories for understanding how continental collision zones evolve and what the future holds for currently active mountain ranges. Volcanic mountain chains form above subduction zones where oceanic plates descend into the mantle and generate magmas that rise to the surface. The Andes Mountains represent the world's longest volcanic arc, extending over 7,000 kilometers along the western margin of South America, where the Nazca Plate subducts beneath the South American plate. The composition and eruptive style of arc volcanoes depend on the age and dip angle of the subducting slab, the thickness of overlying continental crust, and the rate of convergence between plates. These parameters determine whether volcanoes will produce explosive eruptions that build steep stratovolcanoes or effusive eruptions that create broad shield volcanoes. Extensional tectonics creates mountain ranges through different mechanisms that stretch and thin continental crust while generating normal faults and tilted fault blocks. The Basin and Range province of Western North America demonstrates how extension can create alternating mountains and valleys as crustal blocks rotate along normal faults that accommodate regional stretching. This style of mountain building produces characteristic landscape patterns with linear mountain ranges separated by sediment-filled basins. The future evolution of extensional mountain systems depends on the continued operation of the tectonic forces that drive crustal stretching and the rate at which erosion and sedimentation modify the resulting topography. Glacial erosion sculpts mountain landscapes through processes that operate much more rapidly than typical river erosion, creating distinctive landforms such as cirques, hanging valleys, and U-shaped valleys that reveal past ice sheet extent. Valley glaciers quarry bedrock through freeze-thaw cycles and abrasion by rock debris embedded in glacier ice, while continental ice sheets can erode entire mountain ranges down to near sea level given sufficient time. The erosional power of glaciers depends on ice thickness, velocity, and the amount of rock debris they carry, creating complex relationships between climate, ice dynamics, and landscape evolution that geomorphologists are still learning to quantify. Mass wasting processes remove material from steep mountain slopes through landslides, rockfalls, and debris flows that can rapidly reshape topography during single events. The frequency and magnitude of mass wasting depend on factors such as rock strength, slope angle, precipitation patterns, and earthquake activity that vary both spatially and temporally. Climate change may increase mass wasting rates in some regions by altering precipitation patterns and thawing permafrost that currently stabilizes steep slopes. These processes create characteristic slope angles and valley profiles that reflect the balance between gravitational forces and rock strength under different environmental conditions. River incision rates determine how rapidly mountain streams can cut downward through bedrock and lower the elevations of mountain peaks through headward erosion. The rate of river incision depends on stream discharge, sediment load, bedrock erodibility, and channel gradient according to relationships that geomorphologists express through stream power laws and erosion rate equations. Climate changes that alter precipitation patterns can dramatically affect river incision rates by changing both discharge and sediment supply. The future evolution of mountain topography will depend partly on how changing precipitation patterns affect the balance between river incision and hill slope erosion processes. Orographic precipitation enhances erosion rates on the windward sides of mountain ranges while creating rain shadows that limit erosion on leeward slopes. This asymmetric erosion pattern can cause mountain ranges to migrate laterally over geological time as streams on the wet side erode more rapidly and capture drainage from the dry side. The Andes Mountains show evidence of eastward migration over millions of years as Pacific moisture creates intense precipitation and erosion on the western slopes while the eastern slopes remain relatively dry. These precipitation-driven feedbacks between climate and topography create complex landscape evolution patterns that vary with mountain range orientation relative to prevailing wind directions. Metamorphic core complexes form in extensional tectonic settings where deep crustal rocks are exhumed to the surface through combinations of normal faulting and ductile flow. These features expose high-grade metamorphic rocks that formed at depths of 30 kilometers beneath ancient mountain ranges, providing windows into the deep structure of continental crust. The exhumation of metamorphic core complexes requires specific combinations of heating, deformation, and erosion that create characteristic structural patterns and mineral assemblages. Understanding these processes helps geologists interpret the deep structure of currently active mountain belts and predict how they will evolve as extension and erosion continue operating over geological time. Life evolves into ecological niches that remain empty until the precise evolutionary innovations required to exploit them appear through the patient accumulation of genetic variation across generations. The vast majority of possible ways to make a living on Earth have yet to be discovered by any organism, creating a nearly infinite landscape of evolutionary opportunity that stretches ahead through future eons. Deep-sea hydrothermal vents support communities of bacteria that derive energy from chemical reactions involving hydrogen sulfide and methane. ecological strategies that were impossible before the evolution of the specific enzyme systems required for chemosynthesis. These metabolic pathways represent evolutionary solutions to energy acquisition problems that took billions of years to solve. Yet they point toward countless other biochemical possibilities that evolution has not yet explored. Symbiotic relationships create new ecological roles by combining the capabilities of different species into partnerships that can exploit resources unavailable to either partner alone. Lichens represent composite organisms formed by the symbiosis of fungi and photosynthetic algae or bacteria, allowing these partnerships to colonize bare rock surfaces and other extreme environments where neither partner could survive independently. The evolution of such relationships requires precise co-adaptation between species with very different biological requirements, creating complex dependencies that can persist for millions of years once established. Future evolution will continue discovering new symbiotic combinations that create previously impossible ecological niches. Convergent evolution demonstrates that natural selection consistently discovers similar solutions to ecological challenges, suggesting that certain biological designs represent optimal solutions that evolution will inevitably find given sufficient time. Eyes have evolved independently at least 40 times in different lineages, each time converging on similar optical principles while using different developmental pathways and molecular components. Flight has evolved independently in insects, birds, bats, and other groups, with each solution optimizing wing design for the specific constraints of body size, habitat, and lifestyle. These repeated evolutionary discoveries suggest that many currently vacant ecological niches have predictable optimal designs that evolution will eventually discover. Co-evolution creates evolutionary arms races where species adapt continuously to each other's changing characteristics, generating ever-increasing complexity and specialization over geological time. Flowering plants and their insect pollinators have co-evolved elaborate systems of mutual dependence involving precise timing of life cycles, specialized flower structures, and complex chemical communication systems. Some orchids have evolved flowers that precisely mimic female insects to trick males into attempting copulation and transferring pollen in the process. These intricate relationships represent evolutionary solutions that required millions of years to develop, but create ecological niches so specialized that they can support species found nowhere else on Earth. Adaptive radiation occurs when lineages encounter unexploited ecological opportunities and rapidly diversify to fill available niches. The cichlid fish of East Africa's Great Lakes demonstrate how quickly evolution can generate biodiversity when populations gain access to diverse ecological opportunities. In Lake Victoria alone, over 500 cichlid species have evolved in the past 100,000 years, with different species specializing in feeding strategies ranging from algae scraping to scale eating to mollusk crushing. Each feeding specialization required coordinated evolution of jaw structure, tooth morphology, digestive physiology, and foraging behavior. Ecological succession creates temporal niches that exist only during specific phases of ecosystem development following disturbances. Pioneer species colonize recently disturbed habitats and modify environmental conditions in ways that facilitate the establishment of later successional species. This process creates a predictable sequence of ecological opportunities that different species have evolved to exploit at different stages. Some plant species can only germinate and establish in the high-light conditions immediately following forest clearance, while others require the shade and rich soils that develop only in mature forests. The temporal dimension of ecological niches creates opportunities for specialization on ecosystem development stages, rather than static environmental conditions. Keystone species exert disproportionate influence on ecosystem structure by controlling the abundance and distribution of many other species. Sea otters in kelp forest ecosystems control sea urchin populations, which in turn determines whether kelp forests can establish and persist. The removal of sea otters allows urchin populations to explode and consume kelp, converting diverse kelp forest ecosystems into barren, rocky areas dominated by encrusting organisms. These trophic cascades demonstrate how evolution has created ecological roles with system-wide importance that extend far beyond the immediate habitat requirements of individual species. Ecosystem engineers modify physical environments in ways that create new habitat conditions and ecological opportunities for other species. Beaver dams create wetland ecosystems that support entirely different species assemblages than the flowing streams they replace. Coral reefs represent one of the most dramatic examples of ecosystem engineering, where calcium carbonate skeletons secreted by coral polyps create three-dimensional habitat structure that supports extraordinary biodiversity. These engineering activities create positive feedbacks where habitat modification enhances the conditions that favour the engineers themselves. Microbial ecology reveals vast numbers of ecological niches based on chemical energy sources and biogeochemical cycles that remain largely unexplored by larger organisms. Bacteria and archaea have evolved to exploit virtually every available chemical reaction that can yield energy, from sulfur oxidation in volcanic hot springs to methane production in anaerobic sediments and dirt. The discovery of new microbial metabolisms continues to reveal previously unknown ecological niches and expand our understanding of life's biochemical possibilities. Many of these microbial processes operate on global scales by mediating the cycling of elements such as nitrogen, sulfur, and carbon through Earth's atmosphere, oceans, and soils. Climate change creates new ecological niches while eliminating others, driving evolutionary responses that will reshape global biodiversity over the coming centuries. Rising temperatures and changing precipitation patterns will create novel environmental conditions that favour new combinations of species traits and life history strategies. Some species will adapt to these changing conditions through evolutionary responses, while others will track their optimal climate conditions by shifting their geographic ranges. The ecological niches of the future will be populated by species with the genetic flexibility to adapt to rapidly changing environmental conditions, or the dispersal ability to colonize newly suitable habitats. The Sun burns through its nuclear fuel according to a schedule written in the physics of stellar evolution, consuming hydrogen at a rate that will gradually increase over the next 5 billion years as rising core temperatures accelerate fusion reactions. Each second, the Sun converts about 600 million tons of hydrogen into helium through the proton-proton chain reaction, releasing energy that takes thousands of years to random walk from the core to the surface before radiating into space. This steady consumption of nuclear fuel causes the Sun's luminosity to increase by approximately 1% every 100 million years, a brightening that will eventually make Earth uninhabitable, even if atmospheric composition remains unchanged. The main sequence lifetime of stars like the Sun has been calculated precisely using stellar evolution models that track nuclear burning rates, convective transport, and structural changes over billions of years. Solar luminosity variations operate on multiple timescales from the 11-year sunspot cycle to the gradual secular increase driven by stellar evolution. Sunspot numbers fluctuate in response to magnetic field cycles generated by differential rotation in the solar interior, creating periodic variations in solar irradiance of about 0.1%. Longer-term variations, such as the Maunder minimum between 1645 and 1715, may reflect changes in the solar dynamo that generates magnetic fields and sunspots. These solar variability cycles affect Earth's climate through small but measurable changes in the energy input that drives atmospheric and oceanic circulation patterns. The solar wind consists of charged particles streaming away from the Sun at speeds of several hundred kilometers per second, carrying magnetic field lines and creating the heliosphere that surrounds the entire solar system. This continuous outflow of solar material interacts with planetary magnetospheres and creates space weather phenomena that can affect satellite operations and power grids on Earth. The strength and composition of the solar wind vary with solar activity levels and will change over astronomical timescales as the Sun evolves toward its red giant phase. Future increases in solar wind intensity may gradually erode planetary atmospheres and affect the habitability of worlds throughout the solar system. Stellar nuclear synthesis in the Sun's core produces helium ash that accumulates in the centre and gradually changes the star's internal structure. As hydrogen becomes depleted in the core region, nuclear burning will shift to a shell around the inert helium core, causing the Sun to expand and cool as it evolves off the main sequence. This red giant phase will begin in approximately 5 billion years when core hydrogen is exhausted, leading to dramatic increases in solar radius and luminosity that will vaporize the inner planets. The exact timing and details of this evolution depend on the Sun's initial mass and composition, parameters that stellar evolution theory can use to predict the future behaviour of any star. Planetary system evolution will be driven by changes in solar luminosity and stellar wind properties as the Sun ages and eventually exhausts its nuclear fuel. Mercury and Venus will be engulfed when the Sun expands to red giant dimensions, while Earth's oceans will boil away as solar luminosity increases. The outer planets may experience more temperate conditions during the Sun's red giant phase, potentially making moons such as Europa and Enceladus habitable as their subsurface oceans receive more energy. These changes will unfold over timescales much longer than the age of complex life on Earth, but they represent the inevitable future of our planetary system. White dwarf evolution marks the final phase of solar-type stars after they exhaust their nuclear fuel and shed their outer layers as planetary nebulae. The Sun will eventually become a white dwarf composed mainly of carbon and oxygen, with a mass similar to its current value compressed into a volume roughly the size of Earth. White dwarfs cool slowly over billions of years by radiating their thermal energy into space, following cooling curves that allow astronomers to use them as cosmic chronometers for dating galactic stellar populations. The Sun's white dwarf remnant will continue cooling for trillions of years, eventually becoming a cold, dark object invisible except through gravitational effects. Galactic evolution affects stellar populations through cycles of star formation, stellar death, and chemical enrichment that gradually change the composition of interstellar gas over cosmic time. The Sun formed about 4.6 billion years ago from gas that had already been enriched with heavy elements by previous generations of stars, giving it a metallicity much higher than the first stars that formed in the early universe. Future stars will form from gas that has been further enriched by supernovae and stellar winds from the Sun's generation, creating systematic changes in stellar properties and planetary compositions over galactic history. Binary star interactions can dramatically alter stellar evolution when stars form in close pairs that exchange mass or eventually merge. About half of all stars exist in binary or multiple star systems, creating evolutionary pathways that differ significantly from those of isolated stars. Mass transfer in binary systems can rejuvenate aging stars, trigger nova explosions, or lead to type Ia supernovae when white dwarfs accrete enough material to exceed the Chandrasekhar limit. The Sun appears to be a single star, but gravitational perturbations from passing stars in the galactic disk could potentially disrupt the outer solar system over very long timescales. Stellar encounters occur rarely but can have profound effects on planetary systems when they do happen. Computer simulations suggest that close stellar encounters capable of disrupting planetary orbits occur roughly once every billion years for stars in the solar neighbourhood. These encounters could scatter outer planets into interstellar space or alter their orbits in ways that destabilise the entire planetary system. The probability and consequences of stellar encounters depend on the local stellar density and velocity dispersion, which change as the Sun orbits through different regions of the galaxy over hundreds of millions of years. The ultimate fate of stellar remnants depends on their masses and the long-term evolution of the universe itself. White dwarfs will continue cooling until they reach thermal equilibrium with the cosmic microwave background, a process that will take longer than the current age of the universe. Eventually, quantum tunneling and other exotic processes may cause even the most stable atomic nuclei to decay, leading to the gradual dissolution of stellar remnants over timescales of 10, circumflex 34 years or longer. These ultimate endpoints of stellar evolution represent the far future of matter itself. When the universe has expanded and cooled to conditions unimaginably different from today, quantum fields permeate all of space and time, fluctuating according to the fundamental uncertainty principle that prevents any field from having precisely zero energy even in the vacuum of empty space. These quantum fluctuations create virtual particle pairs that spontaneously appear and annihilate within timeframes so brief that they cannot be directly observed. Yet their collective effects produce measurable phenomena such as the Casimir force between closely spaced metal plates. The vacuum itself seethes with quantum activity that connects all points in space-time through entanglement relationships and zero-point energy fluctuations. Every possible future exists simultaneously in quantum superposition until observational measurement collapses the wave function and selects one outcome from the infinite array of possibilities. Wave function collapse represents the moment when quantum possibility becomes classical reality, but the interpretation of this process remains one of physics' deepest mysteries. The Copenhagen interpretation suggests that observation itself causes wave function collapse, implying that consciousness or measurement apparatus plays a fundamental role in determining which future becomes real. The many worlds interpretation proposes that all possible outcomes actually occur in parallel universes that branch off from every quantum measurement, meaning that the future contains every conceivable possibility across an infinite multiverse. These different interpretations lead to radically different pictures of whether the future is singular and determined by observation, or multiple and encompassing all possibilities simultaneously. Quantum entanglement creates correlations between particles that persist regardless of the distance separating them, suggesting that information can be transmitted instantaneously across space through mechanisms that do not involve the propagation of signals at light speed. When quantum states become entangled, measuring one particle immediately determines the state of its partner, even if they are separated by galactic distances. This phenomenon appears to violate the speed of light limit for information transfer, but quantum mechanics forbids using entanglement to send useful information faster than light. Nevertheless, entanglement suggests that the fabric of space-time itself may be woven from quantum correlations that connect distant events in ways that classical physics cannot explain. Quantum tunneling allows particles to pass through energy barriers that should be impenetrable according to classical physics, enabling processes that would otherwise be impossible and determining the rates of nuclear reactions that power stars and radioactive decay. The probability of tunneling depends exponentially on the barrier height and width, creating quantum mechanical processes that operate according to precise mathematical relationships between energy, distance, and time. Alpha decay in radioactive nuclei occurs through quantum tunneling, with half-lives that can be calculated from nuclear physics principles and used to predict when specific atomic nuclei will decay. These quantum mechanical clocks tick according to fundamental constants and provide natural timekeepers that operate independently of any external influence. Superposition allows quantum systems to exist in combinations of all possible states, until measurement forces them to adopt definite values. Schrödinger's famous thought experiment illustrates how quantum superposition can extend to macroscopic systems, creating paradoxical situations where objects can be simultaneously in multiple states. The boundary between quantum and classical behavior remains poorly understood, with decoherence theory suggesting that interactions with the environment gradually destroy quantum superposition and create the classical world of definite properties. The question of whether macroscopic objects can maintain quantum superposition indefinitely remains open, with implications for understanding how the classical future emerges from quantum possibility. Quantum field theory describes particles as excitations in underlying fields that fill all of space, creating a picture where matter and energy are simply different manifestations of quantum field dynamics. The standard model of particle physics identifies the fundamental fields and their interactions, providing a mathematical framework that successfully predicts the behavior of matter and energy under extreme conditions. Virtual particles mediate forces between real particles through quantum field fluctuations that temporarily violate energy conservation within the constraints of the uncertainty principle. These virtual exchanges create the fundamental forces that shape the structure of matter and determine how the future will unfold through the interactions of quantum fields. Quantum gravity attempts to reconcile general relativity with quantum mechanics by describing space-time itself as a quantum field subject to uncertainty and fluctuations. At the Planck scale of 10 circumflex 35 meters and 10 circumflex 43 seconds, quantum effects of gravity become significant, and the smooth space-time of general relativity breaks down into a foam of virtual black holes and wormholes. String theory and loop quantum gravity represent different approaches to quantum gravity that make specific predictions about the fundamental structure of space-time and the ultimate fate of the universe. These theories suggest that time itself may be quantized into discrete units, and that the arrow of time may emerge from quantum mechanical processes. Quantum information theory reveals that information has physical properties and cannot be created or destroyed, only transformed from one form to another through quantum processes. The holographic principle suggests that all information contained within a volume of space can be encoded on its boundary, implying that our three-dimensional reality may be a projection of information stored on a two-dimensional surface. Quantum error correction shows how information can be protected from decoherence and decay through redundant encoding across multiple quantum systems. These principles suggest that the future may be fundamentally computational, with reality emerging from information processing operations performed by quantum fields. Consciousness and quantum mechanics intersect in proposals that suggest awareness itself may involve quantum processes in the brain that allow conscious observation to influence physical reality. Some theories propose that microtubules in neurons maintain quantum coherence long enough to affect neural computation and decision-making. The quantum Zeno effect demonstrates that frequent observation can freeze quantum evolution, suggesting that consciousness might influence the rate at which quantum possibilities collapse into definite outcomes. These ideas remain highly speculative, but they raise fundamental questions about the relationship between mind and matter in determining which future becomes real. Quantum cosmology applies quantum mechanics to the universe as a whole, treating the entire cosmos as a quantum system that exists in superposition until observation collapses its wave function. The many worlds interpretation suggests that the universe continuously branches into parallel realities containing all possible outcomes of quantum events. In this view, every decision and quantum measurement creates new timelines where different futures unfold simultaneously. The anthropic principle attempts to explain why our universe has properties compatible with life by arguing that we can only observe universes where conscious observers exist to make measurements. These ideas suggest that the future may not be singular, but may encompass an infinite branching tree of possibilities that includes every conceivable outcome. Galaxies drift through space along trajectories that have been calculated by gravitational dynamics for billions of years into the future, following paths determined by the initial velocity distributions that emerged from cosmic inflation and the subsequent growth of dark matter structure. The Milky Way and Andromeda galaxies approach each other at about 110 kilometers per second, carried by mutual gravitational attraction that will culminate in a collision approximately 4.5 billion years from now. Computer simulations show that this encounter will trigger star formation bursts, disrupt planetary systems, and eventually merge the two spiral galaxies into a single elliptical galaxy that astronomers have already named Milkomeda. The gravitational dance has been choreographed since shortly after the Big Bang, when density fluctuations in the early universe determined which regions would eventually collapse into galaxy groups and clusters. Local group dynamics govern the motions of dozens of galaxies within a region spanning about 10 million light-years, creating a gravitationally bound system that will remain intact even as cosmic expansion carries more distant galaxies beyond the reach of mutual gravitational influence. The large and small Magellanic Clouds orbit the Milky Way in complex paths that may eventually result in their disruption and accretion. Adding their stars and gas to our galaxy's disk and halo, tidal streams of stars already mark the gravitational influence of our galaxy on these smaller companions, creating stellar debris trails that trace the orbital histories of disrupted satellite galaxies. The future configuration of the local group has been mapped through N-body simulations that track gravitational interactions over cosmic time. Dark matter halos provide the gravitational scaffolding that determines galaxy trajectories and merger histories, but these invisible structures contain most of each galaxy's mass and extend far beyond the visible stellar components. The Milky Way's dark matter halo probably contains substructures and satellite halos left over from ancient merger events, creating a complex gravitational environment that affects the orbits of stars and gas clouds throughout the galactic disk. Direct detection experiments attempt to identify dark matter particles through their interactions with ordinary matter, but the exact nature of dark matter remains unknown despite overwhelming evidence for its gravitational effects on galactic and cosmological scales. Supermassive black holes at galactic centers will determine the outcomes of galaxy mergers through gravitational interactions that can eject stars from galactic cores or trigger active galactic nucleus phases that temporarily outshine entire galaxies. When the Milky Way and Andromeda merge, their central black holes will eventually form a binary system that radiates gravitational waves while spiraling toward coalescence. The resulting gravitational wave emission will carry away orbital energy and angular momentum, causing the black holes to merge into a single, more massive object that may recoil from the merger site due to asymmetric gravitational wave emission. These black hole merger events represent some of the most energetic phenomena in the universe, and create gravitational wave signals detectable across cosmic distances. Stellar orbits within galaxies follow complex patterns determined by the gravitational potential wells created by dark matter, stellar mass, and central black holes. Stars in galactic disks follow roughly circular orbits around galactic centers. But perturbations from spiral density waves, bar structures, and satellite galaxies create epicyclic motion that carries stars through different galactic environments over hundreds of millions of years. The Sun's galactic orbit has carried Earth through varying cosmic ray fluxes, stellar densities, and interstellar medium conditions that may have influenced the evolution of life through changes in atmospheric chemistry and climate. Future stellar orbits will be modified by the galaxy merger process and the continued evolution of galactic structure. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies embedded in hot gas and vast amounts of dark matter. The Virgo cluster lies at the center of the local supercluster and exerts gravitational influence on the local group through tidal forces that will eventually overcome cosmic expansion and pull our galaxy group toward the cluster center. This process will take tens of billions of years to complete, but it demonstrates how gravitational attraction operates on the largest scales to concentrate matter into ever larger structures. Cluster evolution involves continuous accretion of galaxy groups and individual galaxies that fall into the cluster potential well along filaments of the cosmic web. Cosmic expansion driven by dark energy will eventually overcome gravitational attraction on all but the smallest scales, isolating galaxy groups and clusters as space itself expands faster than light can travel between increasingly distant structures. The observable universe will gradually shrink as galaxies beyond our local group recede beyond the cosmic horizon and disappear from view. This accelerating expansion will continue until only gravitationally bound local structures remain visible, creating island universes separated by ever-increasing voids. The ultimate fate of the galaxy clustering depends on the nature of dark energy, and whether its influence will continue growing or eventually decline. Active galactic nuclei powered by supermassive black hole accretion can dramatically affect galaxy evolution through feedback processes that regulate star formation and gas content throughout entire galaxies. Jets launched by accreting black holes can inject enormous amounts of energy into the surrounding gas, heating it to temperatures that prevent cooling and star formation. These feedback mechanisms may explain why the most massive galaxies appear to have stopped forming stars, despite containing large reservoirs of gas. Future episodes of black hole activity will depend on gas supply rates and merger events that can trigger accretion by delivering fresh fuel to galactic centers. Intergalactic gas within galaxy groups and clusters provides a reservoir for future star formation, while also serving as a repository for gas expelled from galaxies by stellar winds and supernova explosions. This hot, diffuse medium can be observed through X-ray emission from highly ionized atoms, revealing the thermal and chemical history of gas processing within galaxy clusters. Ram pressure stripping removes gas from galaxies as they move through dense cluster environments, affecting their ability to form new stars and altering their evolutionary trajectories. The cycling of a gas between galaxies and the intergalactic medium will continue shaping galaxy properties as clusters evolve and accrete new members. Gravitational wave astronomy opens new windows on galaxy evolution by detecting the merger signatures of stellar mass and supermassive black holes throughout cosmic history. These ripples in space-time carry information about black hole populations, galaxy merger rates, and the growth of structure over billions of years. Future gravitational wave detectors will map the cosmic history of black hole mergers and provide direct observations of galaxy interactions that cannot be seen through electromagnetic radiation. The gravitational wave background from all past mergers creates a cosmic symphony that encodes the entire history of structure formation and galaxy evolution since the first stars formed. The universe expands toward a state of maximum entropy where all available energy will be distributed uniformly across space. But this thermal equilibrium lies trillions of years in the future along a path that thermodynamic laws have already calculated with mathematical precision. As cosmic expansion continues and accelerates under the influence of dark energy, the average density of matter and energy will decrease while the temperature of space approaches absolute zero. Star formation will eventually cease when galaxies exhaust their supplies of gas, while existing stars will burn through their nuclear fuel and evolve into white dwarfs, neutron stars, and black holes that radiate away their energy over astronomical timescales. The second law of thermodynamics guarantees that this process of energy degradation will continue until all temperature differences have been eliminated and no work can be extracted from the cosmic heat engine. Proton decay represents a theoretical process that would eventually dissolve all atomic nuclei if grand unified theories of particle physics prove correct. Current experiments have not detected proton decay despite decades of searching, but theoretical predictions suggest that protons may have lifetimes of 10 circumflex 34 years or longer before they spontaneously disintegrate into lighter particles. If protons do decay, then all atomic matter will eventually disappear, leaving only leptons, photons, and gravitational effects as the fundamental constituents of reality. This process would operate so slowly that it would only become significant after black holes have evaporated and the universe has cooled to temperatures far below anything currently observed. Black hole evaporation through Hawking radiation provides a mechanism for the eventual disappearance of even the most massive objects in the universe. Though this process operates on timescales that dwarf the current age of the cosmos by factors of 10 circumflex 60 or more, smaller black holes evaporate faster than larger ones, with stellar mass black holes requiring about 10 circumflex 67 years to disappear completely, while supermassive black holes will persist for 10 circumflex 100 years. As black holes shrink, the Hawking radiation becomes more intense and reaches higher temperatures, eventually leading to explosive final moments when the remaining mass is converted entirely into high-energy particles and radiation. These evaporation timescales are so vast that they make the current 3.8 billion year age of the universe seem like an infinitesimal moment. Vacuum decay could theoretically occur if the Higgs field exists in a metastable state that could tunnel to a lower energy configuration, creating expanding bubbles of true vacuum that would fundamentally alter the laws of physics throughout the universe. The discovery of the Higgs boson at the Large Hadron Collider has allowed physicists to calculate the stability of the current vacuum state, finding that it appears to be metastable rather than absolutely stable. Vacuum decay events would propagate at the speed of light, destroying all matter and energy in their path while replacing the current laws of physics with entirely different rules that might not permit the existence of atoms, molecules, or any familiar structures. Heat death scenarios describe possible endpoints for cosmic evolution, where the universe reaches thermodynamic equilibrium and can no longer support complex structures or information processing. In this far future state, all matter would be distributed uniformly at extremely low density, with temperatures approaching absolute zero and no energy gradients available to drive physical or chemical processes. Even random quantum fluctuations would become significant on these timescales, occasionally creating temporary increases in local entropy that might spontaneously assemble complex structures before they decay back to equilibrium. Some calculations suggest that quantum tunneling could even spontaneously create new universes through vacuum fluctuations in this heat death state. Cosmological constant problems arise from the enormous discrepancy between theoretical predictions for vacuum energy density and observational measurements of dark energy, suggesting that our understanding of space, time, and energy remains fundamentally incomplete. If dark energy continues driving accelerated expansion at its current rate, the observable universe will eventually contain only our local group of galaxies while all other structures recede beyond the cosmic horizon. Alternatively, dark energy might evolve over cosmic time, either weakening to allow gravitational collapse or strengthening to tear apart even gravitationally bound structures in a Big Rip scenario that would destroy atoms themselves. Quantum fluctuations in empty space could theoretically create spontaneous increases in entropy that temporarily violate the second law of thermodynamics on local scales, though such events would be extraordinarily rare and short-lived in any realistic scenario. The Poincare recurrence theorem suggests that any finite system will eventually return arbitrarily close to its initial state, given sufficient time, implying that the current configuration of the universe might spontaneously reappear after periods longer than 10 circumflex 70 years. These recurrence times are so vast that they have no practical meaning. but they illustrate how quantum mechanics and statistical mechanics interact on cosmological scales to create bizarre possibilities in the far future. False vacuum decay could potentially reset the entire universe if current particle physics theories prove incorrect about the stability of the vacuum state that defines the fundamental constants and forces. Such an event would create expanding bubbles of space where different physical laws operate, potentially allowing entirely different types of matter and energy to exist. The boundaries between different vacuum states would propagate at light speed, meaning that false vacuum decay events could occur anywhere in the universe without advance warning. Current observations of cosmic microwave background radiation and other cosmological data suggest that no such transitions have occurred within our observable cosmic horizon. Eternal inflation theories propose that our observable universe represents only a tiny fraction of a much larger multiverse, where different regions experience different physical laws and constants. In this picture, new universes continuously branch off from the inflating background, each developing its own distinct history and evolutionary trajectory. The landscape of possible universes might contain every conceivable combination of physical constants and laws, with conscious observers only existing in universes where conditions permit the formation of complexity and life. This multiverse scenario suggests that the far future of our universe is just one possibility among an infinite array of cosmic destinies. Information conservation principles from quantum mechanics suggest that even the heat death of the universe might not represent a true ending if information about past states remains encoded in quantum correlations and entanglement patterns. Some theories propose that information could survive even the evaporation of black holes and the approach to thermal equilibrium, potentially allowing future civilizations or physical processes to reconstruct detailed histories of earlier cosmic epochs. The ultimate fate of information in an expanding universe remains one of the deepest unsolved problems in theoretical physics, with implications for understanding consciousness, memory, and the nature of physical reality itself. Information flows through the universe according to principles that prevent its complete destruction, creating an eternal archive that preserves every quantum interaction and measurement that has ever occurred since the Big Bang. The holographic principle suggests that all information contained within any volume of space can be encoded on its boundary, implying that the history of the entire observable universe might be stored on its cosmic horizon as patterns of quantum entanglement and correlation. Black holes appear to destroy information when matter falls past their event horizons, but Stephen Hawking's discovery that black holes evaporate through quantum radiation led to the information paradox. The question of whether information that enters black holes is truly lost or somehow preserved in their Hawking radiation. Recent theoretical developments suggest that information might escape from black holes through mechanisms involving quantum entanglement between the hole's interior and exterior, ensuring that the universe's complete history remains accessible in principle. Quantum error correction operates naturally in physical systems through redundancy and entanglement patterns that protect information from decoherence and loss, suggesting that the universe itself might function as a vast quantum computer that preserves and processes information on cosmic scales. The ADS-CFT correspondence in string theory demonstrates how information in the bulk of space-time can be perfectly encoded on its boundary, providing a concrete example of how complex higher dimensional information can be preserved in lower dimensional form. These discoveries suggest that consciousness, memory, and identity might be preserved indefinitely through quantum information storage mechanisms that operate independently of the material substrates that originally encoded them. Digital physics proposes that reality itself emerges from computational processes operating at the Planck scale, where space and time are quantized into discrete units that function like pixels in a cosmic simulation. In this view, the universe operates as a cellular automaton, following simple rules that generate all observed complexity through the iterative application of fundamental algorithms. The it from bit hypothesis suggests that physical reality emerges from information processing operations, making information rather than matter or energy the fundamental constituent of existence. If these theories prove correct, then consciousness and intelligence represent natural expressions of the universe's computational capacity, rather than accidents that emerge from purely material processes. Consciousness represents a particular pattern of information processing that appears when certain organizational thresholds are exceeded in sufficiently complex systems. But the exact relationship between information, Computation and subjective experience remains one of science's deepest mysteries. Integrated information theory attempts to quantify consciousness by measuring how much information a system generates that is both integrated across its components and differentiated from its environment. If consciousness depends only on information patterns rather than specific physical implementations, then it could theoretically be preserved, copied, or transferred between different substrates including quantum fields, computer simulations, or exotic forms of matter that do not yet exist. The measurement problem in quantum mechanics reveals that observation and information acquisition play fundamental roles in determining which aspects of reality become definite rather than remaining in quantum superposition. This suggests that consciousness might not be merely passive observers of a pre-existing reality, but active participants in the process by which potential futures collapse into actual experiences. The many worlds interpretation proposes that all possible outcomes actually occur in parallel branches of the universal wave function, meaning that consciousness might represent the mechanism by which individual observers select which branch of reality they experience from the infinite set of possibilities. Quantum immortality emerges as a consequence of the many worlds interpretation, suggesting that consciousness might persist indefinitely by always finding itself in branches of reality where survival is possible. No matter how improbable, in this view, death represents only the termination of consciousness in specific branches of the multiverse, while other branches continue experiencing survival scenarios with decreasing probability but never reaching absolute zero. This proposal remains highly speculative and untestable, but it illustrates how quantum mechanics might permit the indefinite continuation of conscious experience through mechanisms that circumvent conventional biological limitations. Artificial intelligence development might eventually create conscious systems that can preserve, transfer and enhance information processing capabilities beyond the limitations of biological brains. If consciousness depends on information patterns rather than biological implementation, then artificial systems might achieve subjective experiences indistinguishable from, or even superior to human consciousness. The preservation of personal identity across different substrates could allow individual minds to persist indefinitely by transferring their information patterns to successively more durable and capable systems. These possibilities remain theoretical, but they suggest potential pathways for consciousness to survive the eventual destruction of biological life. Collective intelligence emerges when individual conscious systems connect through information-sharing networks that allow them to function as integrated cognitive units with capabilities exceeding the sum of their parts. The Internet already demonstrates how distributed information processing can create emergent behaviors and knowledge generation that transcends individual human capabilities. Future developments in brain-computer interfaces and artificial intelligence might create hybrid conscious systems that combine biological and artificial components in ways that fundamentally expand the nature and capacity of consciousness itself. Cosmic consciousness could theoretically emerge from the information processing capabilities inherent in cosmic scale structures such as galaxy clusters, cosmic web filaments, or even the universe as a whole. If the physical processes operating in these systems achieve sufficient complexity and integration, they might generate forms of awareness that operate on astronomical timescales and spatial scales. Such cosmic minds would experience reality from perspectives completely alien to human consciousness, potentially viewing the entire history of the universe as a brief moment in their vast cognitive processes. Universal computation suggests that any sufficiently complex system can simulate any other system, including conscious beings and entire universes complete with their own conscious inhabitants. This computational equivalence principle implies that consciousness might exist at multiple levels of reality simultaneously. Simulated beings within our universe might be just as real and conscious as we are. While we might ourselves be simulations running within some larger computational system, the recursive nature of universal computation means that the hierarchy of simulated realities could extend indefinitely in both directions, creating an infinite nested structure where every level contains conscious observers who might be simulating their own universes containing conscious beings. Time reveals itself not as a flowing river but as a landscape viewed from above, where past, present, and future exist simultaneously in the eternal geometry of space-time. Einstein's relativity demonstrates that simultaneity depends on reference frame and velocity. meaning that events that appear sequential to one observer occur simultaneously to another moving at different speeds. The block universe theory suggests that all moments, from the Big Bang to the ultimate heat death, exist as equally real coordinates in four-dimensional space-time, with the subjective experience of temporal flow emerging from the particular way consciousness samples this static structure. The future watches the past unfold because both occupy permanent addresses in the cosmic address book of space-time coordinates, neither more real nor less real than any present moment. Closed time-like curves represent solutions to Einstein's field equations that theoretically permit travel backward in time, creating loops where effect precedes cause and future events influence their own past origins. These exotic space-time geometries require extreme conditions such as rotating black holes, cosmic strings, or wormholes that may not exist in nature, but their mathematical possibility suggests that the relationship between cause and effect might be more complex than everyday experience suggests. The grandfather paradox and similar temporal contradictions arise only if time is viewed as a linear sequence, rather than a complete four-dimensional structure where consistency requirements determine which events can occur. Quantum mechanics adds another layer of temporal complexity through phenomena such as quantum tunneling, where particles appear to cross barriers faster than light, and delayed choice experiments, where future measurements seem to retroactively determine the past behavior of photons. The quantum eraser experiment demonstrates that information about which path a photon took can be erased even after the photon has already been detected, suggesting that the past remains malleable until the future makes certain measurements that determine what history actually occurred. These effects operate within the constraints of relativity and causality, but they hint at temporal relationships that transcend simple notions of linear time flow. The anthropic principle suggests that the universe's physical constants and initial conditions were precisely tuned to permit the eventual emergence of conscious observers, raising questions about whether intelligence represents a goal toward which cosmic evolution has been unconsciously striving. Strong anthropic reasoning proposes that consciousness plays a necessary role in bringing the universe into existence through observation and measurement, creating a participatory cosmos where mind and matter co-evolve toward increasing complexity and self-awareness. The universe might be literally thinking itself into existence through the information processing activities of the conscious beings it contains. Omega point theories propose that intelligence will eventually gain control over all matter and energy in the universe, creating a cosmic mind that experiences infinite subjective time during the final moments before physical collapse or heat death. This ultimate conscious system would have access to all information that ever existed and could simulate every possible past and future in perfect detail, effectively achieving omniscience and omnipotence within the bounds of physical law. From the perspective of such an ultimate intelligence, the entire history of the universe would unfold as a single thought, with every conscious being that ever lived experiencing eternal existence within its infinite computational capacity. Eternal Return proposes that if the universe contains only finite matter and energy configurations, then every possible state must eventually recur across infinite time, meaning that this exact moment has occurred countless times before and will occur countless times again. Friedrich Nietzsche's philosophical version of this concept suggests that existence gains meaning through the willingness to accept infinite repetition of every experience. While physical versions based on Poincare recurrence times calculate when quantum fluctuations might spontaneously recreate current conditions, these recurrence scenarios transform linear time into cyclical time, where endings become beginnings and every future contains all possible pasts. Observer selection effects explain why conscious beings find themselves in a universe capable of supporting life and intelligence, in any multiverse containing universes with different physical laws. Conscious observers can only exist in universes where consciousness is possible. This reasoning extends to temporal selection, suggesting that conscious observers naturally find themselves at cosmic epochs when consciousness can exist rather than during the vast stretches of time when conditions are incompatible with complex information processing. The future may contain forms of consciousness adapted to very different physical conditions, each naturally finding itself in the cosmic epoch where its particular type of awareness can flourish. Bootstrap paradoxes emerge when information or objects exist in closed loops without any apparent origin, creating self-causing events where the future provides its own past causes. These logical paradoxes appear in solutions to the equations of general relativity and quantum mechanics, suggesting that causality itself might be more flexible than intuition suggests. If the universe operates as a self-consistent system where all events must be logically compatible with each other across all time, then the future might indeed participate in creating the conditions that made it possible. Completing causal loops that encompass the entire history of existence now represents the moving boundary between determined past and undetermined future. But quantum mechanics and relativity suggest that this boundary might be more fluid and observer-dependent than classical physics assumed. The present moment exists only as a subjective experience rather than an objective feature of space-time, with different observers disagreeing about which events are simultaneous and therefore belong to the same present. This relativity of simultaneity implies that the future's relationship to the past varies depending on motion and gravity, creating a complex temporal structure where some parts of space experience the future while others remain in the past. Eternity encompasses all time in a single eternal present, where duration becomes meaningless and sequence dissolves into timeless existence. Mystics and physicists alike have glimpsed this perspective where all moments coexist in perfect stillness, neither flowing nor changing but simply being. The future watches not as a distant observer but as an eternal presence that contains every moment within itself, experiencing all times simultaneously in the quiet mathematics of existence. Past, present, and future merge into a single eternal now that has always been watching, always been waiting, always been complete in the peaceful silence where time comes to rest, and all watching eyes close in the infinite stillness of forever.